Well, good afternoon. We're past 12 o'clock to everyone. Let me start by saying what a complete thrill, what a delight it is for our department to be hosting an event actually in person. It's too long to remember since the last time we had such a thing. So enormous thanks to Pete and Matthew for courageously deciding to go ahead and put on this event. Enormous thanks also. I know that many of our PhD students are taking part. This is absolutely wonderful. It's really a delight to have the chance to hear you, and indeed all our other speakers. I'm particularly delighted as well that we are even able on this occasion to welcome an external speaker, Dr. Peter Bray from Reading, who's done really important work on archaeometallurgy, issues like lead isotopes, copper, provenance, these kinds of issues. We're absolutely delighted to welcome Peter here to join us today. And let's enjoy this occasion. It's fantastic that we're going ahead live and in person, and I will keep quiet and I will enjoy the rest of the afternoon with you. But many thanks indeed again to everyone who's here. It's an absolute treat.
Matthew, would you like to say a few words to open the conference?
Yes. Thank you very much. Do I have to stand here?
Just anywhere really around there should be fine.
All I wanted to do really was to basically reiterate what Professor Gibson has just said in his introduction, and to say that it's really nice to see people in the flesh again for the first time in a very, very long time. Nothing can replace that, having spent a lot of time on Zoom, as we all have over the last few months. I gave a conference paper at the University of Warsaw on Friday afternoon, and a thing called Google Meet, which I had never come across before, and hopefully will never come across again. And it's a good opportunity to do a little bit of flag waving for the department, to acknowledge the sterling work that's been done really over the last decade or so in the field of archaeological materials, to show that we can do that sort of work of really high quality here in Liverpool, and to celebrate the fact. And I think I look forward to a very informative day. Thanks very much.
Well, we're going to begin the conference in a moment with our first speaker, who is, I think he's with us, who'll be joining us in a second anyway, who's going to be talking to us, appropriate enough, by beginning a materials conference with something about some of the earliest technologies that we look at, looking at stone technologies and thinking about the ways in which lithic functional analysis can just explore the beginnings of combinatory technologies. Let me just share this. Okay, start from there. And Chris Scott will be here momentarily, I'm sure. It's quite exciting to have someone who's actually not physically here, but might be physically here at any moment. I'm sure it'll all come together. Whilst I'm here, I just want to say thank you for everyone, and I hope everyone joining online is able to hear us. If you have any questions or anything, you can ask them via the chat. If you've got a Google account on YouTube, or you can ask them by emailing me at peter.com at liverpool.ac.uk. That's all. There's a note in the chat to that effect anyway. So here he is now. He's joining us, Chris Scott, who's one of our PhD students here. Welcome, and take it away, Chris.
Good afternoon, thank you. Am I okay to do mask? Is that...
Yes, when you're talking, that's fine.
Okay. Thank you for that introduction, and for organising the conference, and also for inviting me to speak as well. So today I'm going to give you the talk titled Joined-Up Thinking, Lithic Functional Analysis and the Detection of Combinatorial Culture, which at this stage I imagine means very little to anybody who's actually watching. Before I try and make sense of my title, I'm going to go on a small philosophical tangent. So today the conference is titled Ancient Technology and Materials. And we're concerned with how our ancestors engaged with and transformed raw materials in the past into the tools that they needed to survive. Essentially, it's about inferring behavior from that process. It's archaeology. This should come as no surprise. That's what we do. We infer human behavior from the material remains. I come from a part of the archaeological family called evolutionary anthropology. This is Professor Sinclair's territory, or Jenny French, some of you may have met in Matt Grove. Just like the rest of the archaeological family, we infer human behavior from the material record, so the archaeological record and the fossil record. Arguably, however, we have a slightly different goal, a slightly different agenda, in that we're interested in what makes actual humans unique. What is it that makes us as a species unique? So rather than being interested in one particular group or another group, we're interested in as a species level. And to put that into the context of today's conference, in some ways, we're interested in the raw material of actually being human. Now, you may well ask, excuse me, what is the return? What is the value of evolutionary anthropology? Well, for us to work out what makes us unique and what makes us human, we have to look at other animals. We have to perform zoological and ethological studies. And decades of research into looking at animal behavior has shown that, as you would expect, there are significant quantitative differences. These are things that we do better than other animals. So I think we would all agree human language is a better form of communication, and certainly human technology in the context of today's conference. These same decades of research have, however, shown it's very difficult to pin down qualitative differences. These are things that we do that are completely unique, things that are not seen in any way, shape, or form outside of humanity. Today, you're going to hear talks about mirrors, which we've used in evolutionary anthropology to demonstrate other animals have got self-awareness, using the Gallup mirror test, where they put a chimpanzee in front of the mirror with a red dot on it, and it will always find it. And they actually, I think, use them to groom themselves as well, if you leave them with them. You're going to hear about coins and a Greek currency. Again, we know that chimpanzee societies work with currency. They groom each other, they build up debts, and they can spend those debts however they like. So you don't have to buy more grooming back. You can have support in an argument and a fight later on if you like. And you're also going to hear about forgeries and deception. And again, primate society is almost always about deception in some way. It's about convincing one of your friends that something is different to how they expect for your benefit. To me, this situation of only really having quantitative differences, it shows us how close we are to the animal world and how close we are to nature. And this human reconnection with nature, I think, is essential for nature itself, but I also think it's very good for us as humans. There's a Native American proverb, a person's heart away from nature grows hard. The Japanese have something called forest bathing. It's becoming more and more widely known and accepted that if humans accept themselves as part of nature and spend time in it, it's much better for us. So that's just a small philosophical digression as to why I think evolutionary anthropology is important and to frame some of my research. So my research then, combinatorial culture. It'll become clear what that is, hopefully. Thinking about what makes us unique then, human unique behaviors, culture has long been discussed as this thing that makes humans unique. Other animals don't have it. When I use the term culture, all I really mean is behavior that is learned from another member of your group. Values, knowledge, and then other members of the group can learn it from you. It passes on down the generations. A key part of culture and human adaptation, as we know, is technology. Technology is cultural because we learn it from other people. And it's definitely the human adaptation because without it, we wouldn't be able to extract calories from the environment or stay warm on an evening. If we were to go into the street today and ask 100 people, what do you think makes us uniquely human? Quite a chunk of them are going to come back and they're going to say tool use, tool behavior. This was kind of crystallized in the mid-60s when Louis Leakey discovered the skeletal remains of what he termed Homo habilis. And he found it in association with stone tools. Slightly larger cranial capacity, as you can see here, association with stone tools. And he basically placed it at the start of our genus. And he said, the human tool paradigm was kind of born. Now, this is probably the shortest paradigm in history because in the same year, 1964, Jane Goodall went out to Gombe and discovered chimpanzees manufacturing and using tools, an incredibly complex tool behavior. But it still exists, this tool behavior concept is still there sometimes. We know from continued research that actually now tool behavior is almost more the norm than is the exception. I've seen bees using tools. I've seen, almost every study they test an animal to see, it seems to be able to do it. Let's just pull back from tools back to culture, because that's really what I'm talking about. We also know that culture as a set of learned behaviors that are passed on can't really be seen as unique either to humans anymore. This is a map of the different chimpanzee groups that are found, and essentially they've got different profiles of behavior which persist over time. They learn them from each other. So we can't say that culture is unique to humans. It's like a quantitative thing. We have different culture. So this allows us to ask a much more interesting question about how is human culture unique. So just back to the tool slightly, and probably one of the funniest photos I've ever seen. I don't know why they couldn't find a scale and they had to use a guy with a moustache. It's brilliant. But we know that from all these studies that animal tool behavior is extremely complex. They have tool sets that they use sequentially, they manufacture them, there's forward planning, there's social learning. What we don't see though is, what we do see is they're limited to reductive technology. And this means that to get what they want, they can only remove things. So they can take a branch and take the bits off that they don't want. We don't see any construction of tools, no addition of components to get to the tool that they want. If we ever think about that for a second, this reduction versus addition or combination of things, just ask yourself this question: how much complexity or variation in tools do you think you could achieve just using reduction? Can anybody even think of a couple of technologies which are totally reductive in terms of human technology? Carve you a spoon, maybe. That's about it. Okay, so this combination, and crucially, a big part of that combination is recombination. It's the ability to take something you've learned from this technology and then deploy it in another domain. This is the key to the open-ended complexity of human technology. So you end up not just with more tools, you end up with novel tools. They're also better tools. You end up with things like this. Increased reach, leverage, force application, things that you just could not do through reductive technology. This leads to the central hypothesis then of my thesis. I accept that culture and technology is a human adaptation and that it's just quantitatively different. The key central point is that any adaptation needs variation. It's like a central component of any adaptation. If you imagine a species of clones living on an island, if the environment was to change and that clone species has no players it can put forward, no novel adaptations it can try out, it will just go extinct. It cannot track environmental change. And that is the same for anything really, if it's going to be an adaptation. So this leads to the crux of it, and that is that human adaptation through culture could actually only occur once our culture was based on combination. And it is this combination of technological elements which provides the variation that is needed. There are other parts of culture than technology which are deeply combinatorial. They're all kind of linked together as well. I'm not going to spend too long on this because it's a whole thesis in itself, but language is deeply combinatorial. When we think about how we make a single word, we have phonemes, sounds, which we shape into words. We then combine those words into sentences, into meaning. And then through just a couple of hundred words, you can have the entire works of Shakespeare. You just use recombination to get there. There's another element of language which is combinatorial, and that is its use of symbols. A symbol is communicating something that has nothing to do with the signal. So we could decide that my bottle here means Wednesday morning. There's no link to it. It just becomes a symbol for it. For us to do that, though, for us to all agree that, we would have to combine our minds. So we see then we have this combination. Again, we see recombination because we could decide next week, no, we don't want it to be Wednesday morning. We want this to mean Friday afternoons. We could recombine it as we need to. It becomes adaptive and recombinable. The cooperation thing, I'm just going to breeze over a little bit. We kind of touched upon it with the symbols, with that agreement of mind. If we accept then that combinatorial culture is a human adaptation, we've got to go and look for it. Language doesn't fossilize. We have Sumerian tablets, 6th century BC, pretty short language before that. The cooperative behaviors and symbolism, incredibly difficult to spot archaeologically. So we're left with the durable archaeological record then, and this is tools made of more than one thing. Sometimes get called composite tools, or in Larry Barham's book, he calls it combinatorial technology. And this is hafting a stone tool to a wooden handle or jamming it into the end of a bone, simple as that. This detection of hafting didn't really receive much nobody was really that bothered about it for a long time. And then my supervisor, Dr. Juliet Spedding, based over in Tresio Lab, she started looking into this, and this 2010 is the publication of her thesis. And she looked at the formation of detectable patterns of wear. Sorry, I've jumped ahead a little bit, let me back up. So the detection of hafting then, we're clearly not going to have the wooden bits and the bindings. They're all going to be gone through taphonomic loss. It's just going to be the lithics. There is a method of telling what a lithic has been used for in the past, and this is through what we call microscopic use wear analysis. Every time we use a stone tool, we alter the way the edge is, we fracture the edge differently, and we also polish the surface of it, which can be detected under a microscope. And depending on what you've used it for, you get a different kind of pattern of evidence. So the first person to do this, as I was saying, is Vera Rotz. She looked at how these patterns of evidence develop when a tool has been hafted like this. But she was looking at, as the top picture shows, simple flake-based technology. So the edges of the stone tool hadn't been worked. It was a very clean kind of thing to look at. And my research extends this to look at the bifacial lithics. These are tools that have been worked on both sides, so they're a much more complicated kind of geometry to work with. These are kind of Acheulean fossil directeur kind of idea. These ones here are from Boxgrove that you can see, which is the site that I'm trying to look at, but obviously lost access through COVID. They're 500,000 years old, and they look like they were made yesterday. They are incredibly fresh. So that is essentially what I'm trying to do, is work out a method of seeing whether these stone tools were ever attached to a handle. The evidence that I look for then, there are microfractures. This is how the edge breaks away in tiny things. I've got 13 variables for that. You can see polish in the top right-hand corner. This is that surface abrasion I was telling you about. This is an increase in reflectivity as it polishes up. And then you've got crushing and striations and things that you can see there. So there's an incredible amount of variables that you have to try and control for just when you're looking at the evidence. There's also the variables that I have to test, and this is how the tool was hafted, or how the tool was handheld, or how the tool was wrapped, as you can see from there. The different materials I use, whether I use animal bindings like these ones here, or whether I use vegetal bindings. So as you can see there, that's lime cordage. And then there was chopping down trees, freshwood working, hide working, digging. All these experiments have to be controlled for. I also had to bury a load of tools, leave a load in a river, throw a load in a bag and carry them around for 6 months, just to simulate as many different wear processes as possible. Finding and recording the wear then, to know that the wear that's been produced is linked to the thing I'm after, the hafting, I need to know what the rock looks like first. So this means using pre-use recording, and you can see these grey images are from RTI, reflectance transformation imaging, which is a relightable model, which I then control and produce these from. I take overlapping digital images of the edge, and I perform microscopic analysis before they're used to make sure any anomalous wear I understand. I then go out, I chop a tree down, or I dig a hole, I strip the lithics out, clean them up, and then I go make a new model, perform new microscopic analysis, carry out all the variables I mentioned, and then I color code the evidence types onto these models. And the idea being that I'm not just interested in the types of evidence that form, it's their spatial relationships to each other, which may be interesting. It's the locations of where they form as much as how of what they form. So this pretty much sums it up then. There's no single diagnostic piece of polish, no single diagnostic scar or striation that's ever going to tell me what I'm looking at. It's a constellation of evidence, and it's always going to be a balance of probability with use wear analysis. Currently, I've got 35 tools which have turned up to my lab just in bags, as if from an archaeological site. They've been used, I think, in some way, and I have to perform a report to say these are being used and hafted and extract as much information out as possible. That's currently what I'm working on. That will show whether this method, how reliable this method is. I already know that because of the complexities, it's not going to be a single, this tool is, this tool isn't. What I'm trying to develop is more of an assemblies level approach, whereas if you gave me 50 tools and hafting it have existed in that culture, I'm going to get 1 or 2 tools or 4 or 5 tools, which are really clear evidence. And they're the ones that I'm really going to look for. I think it's a more secure way to progress, because if this idea of combinatorial culture is present, then they're not just going to be hafting 1 or 2 things. They're actually going to be taking the time to make all their tools better. We actually see this at Biache I don't know if I'm pronouncing that right. It's a French site. But you get hafting there, and they're not just hafting the tools that they need to haft, the digging tools and the arrows and things. They're actually hafting everything. So as soon as this technology arrives, because the tools are so much better, it gets taken up. So I think the assemblage level thing should hopefully work out. And there we are. Thank you for listening to me. I don't know how long I ran on. Any questions, please?
If anyone has any questions, do speak up. The microphone should pick you up yourselves. But if your voice is a bit weak, then you can always repeat your questions as well. Anyone got any questions?
How much of a challenge to these microware approaches is our multiple uses? Do you think we'll be able to see quite long histories of a tool being used for different things?
Yeah, it's a good question. There's 2 issues. There's, as you say, there's using a tool for more than one thing, so you have overlapping evidence. So you'll only see the last use. And then there's also resharpening. So you're taking off the resharpened edge. One of the benefits to actually looking for hafting is because the area that is hafted where the evidence develops is actually protected from other wear, and it actually only becomes exposed once you dehaft the tool. It's not removed through resharpening. So it's a challenge overall for microware. And certain activities, butchery, for instance, is very difficult to spot. If you were to butcher an animal and then chop a tree down with it, all I'm going to see is you chopped a tree down with it. But as I say, the evidence for hafting is actually much more secure in that respect, which is kind of handy.
So a couple of questions, I suppose. So one of them is all about, I suppose, technique. And so the way in which things are performed is not purely determined by the physical shape of the tool, but by the techniques of use that the individual brings to it. And can one pick up that sort of difference? And do you think that we might hope towards looking to a standardization of technique as people learn and share their best ways of doing things?
Yeah, you've actually hit onto something. There's a further point there. So there's the gesture of how you use the tool, and that will affect how wear forms. The main thing that actually affects it is the pressure, really, in the haft. So actually the angles and things I've experimented with, and that doesn't seem to make as much difference. But as you would imagine, if I really hit this thing, it leaves a lot of wear. If I just work gently with it, it doesn't leave very much wear. But the gesture thing goes further than that, and that is that when I first started hafting these tools at the beginning of my PhD, I wasn't very good at it. And as a result, the stone moved around a lot in the haft and left loads of wear. You could spot them without a microscope. As I've become more and more familiar with the process, the wear is less and less. And I know that the blind test that I've got, the colleagues who have made the blind test for me are experts. They're 2 of the best people in the world. And the evidence is scaled back 50%, 60% that I'm having to interpret. And it's good to know that, because then when I go to the archaeological record, I have to assume they would have been experts. So that's the kind of the eye-opening thing, is working with the experts in terms of the gesture of hafting seems to be more important.
Second one, obviously we've been using hafted tools for tens of thousands of years. Mm-hmm. How easy is it for us to imagine the first hafts? In a sense, how is our sense of how things might have been combined together driven by that experience we have of what hafts look like today, which are obviously partly driven by the sorts of materials we halved?
Yeah, I think some of the most basic hafts you still see in use are people just jamming a rock into the end of a bone. and they use it with smaller flake-based technology. So that, I think, would have just looked the same. And luckily, that leaves quite diagnostic marks because it really grinds the stone tool up. Moving to more of the techniques here that I've looked at, yeah, you are right, we're influenced by what we see the ethnographic record. We make the tools to look a little bit like those, we get them to work. So yeah, there is a little bit of guesswork there. Some of the evidence, some of the friction-based evidence, I mean, we see just very distinct wood polish in the middle of a tool, you know, the central region of a tool. So you can see number 40 there, that is distinct wood polish, and 39 here. Sorry, it's not, it's this side, 47, this is the wood polish region here. It's very difficult to explain how wood polish would get there through any other use than a handle being there. So it's just a matter of previously people haven't bothered looking in the central regions of the tools because they're in front of the microscopes. It's actually one of the main problems. But yeah, does that answer your question? Yeah. Any more?
I could go on forever, but I'm not. Sorry.
Does anyone else have any questions? If not, then Chris, thanks very much for opening the conference. And okay, so our next speaker, we're going to move. I've stopped. I've pressed the wrong button there, man. There we go. Excuse me. Too keen. A moment of technical glitch. Remember not to unshare the screen next time. It's an opportunity to advertise our new experimental centre at least. So that will, okay. Right. So our next speaker is Lis Thomas, who's going to be talking to us about Egyptian mirrors. A bit of a change in tack, but hopefully something which will be a bit of fun as well. So let's get going. Lis, welcome to the conference.
Hi everyone, as Pete said, I'm Lis. So I'm a first year PhD student in the department. My research is AHRC funded, and I'm looking into the metallurgy of ancient Egyptian mirrors. So that's how they were made, what they were made of, and then I'm going to try and fit that into Egyptian culture and society. So first, a bit about mirrors. So they're not like modern day mirrors. They're not made of glass. They're actually metal sheets, discs, that were put into handles. Because they were made of metal, they were reserved typically for the elite of society, because metal was an expensive commodity. This is exemplified by the quote, where lower classes would have used water to see their reflection, and then the higher classes were able to afford mirrors. So mirrors are typically found in tombs close to the deceased, by their feet, within the mummy wrappings on their chest, in front of the head, behind the head. They've also been found in boxes with other cosmetic items, such as makeup and wigs. Mirrors have strong religious iconography links. So the disc itself was also viewed as the sun disc. This is partly because of the color. So the metal, they were made of copper primarily, so the metal would have been quite orange, sometimes yellow, red, and white, whereas the sun obviously is those kind of colors as it goes through the sky. So that's linked to the sun god Ra in Egyptian mythology. Also on the handle, they often showed lotus flowers. So lotus flowers are linked to rebirth in the creation myth. And also you might see the goddess Hathor, who's the cow goddess, her face. And she was linked to women, fertility, and beauty within Egyptian culture. So here are some images of mirrors. On the left, you have a tomb scene. This is a procession where people are taking different goods to the tomb of the deceased. This is just a small section of it. As you can see, there's a golden mirror at the top there. On the top image, this is a coffin frieze. So coffin friezes were common in the Middle Kingdom in Egypt, and objects that they wanted in the afterlife were put as images on the coffins to ensure they had that. In Egypt, you didn't have to have the actual object for you to then have it in the afterlife. It was kind of magic. So as long as you had an image of it, you would have it. Also, mirrors are seen on stela. As you can see, the small little red disc here. Then in the middle, so this one is an actual mirror. It's green now due to corrosion, and it has some textiles on it. So often mirrors were wrapped in textiles to be deposited into, primarily to protect the reflective surface. If you touch it, you put it down, it's going to tarnish, you won't be able to see yourself in it. But also it was thought that mirrors had magical powers, and things like part of your soul, the car, could live in it and help you achieve eternal life. So in order to suppress some of those magical powers so they couldn't do their own thing, the reflective surface was covered. On the right, you have a wooden model mirror. So like I said before, you don't actually have to have the real thing to have it. So instead of a depiction, some people had wooden models. This one's covered in gold leaf to try to recreate the color that the metal might have been. Wooden models were common in Egyptian tombs. So this is, and there's different forms. There's this one that looks like an actual mirror, but there's others where the woman's like holding one up in front of her, and others where they're just in a bag over someone's shoulder. So there are some issues in terms of research into Egyptian mirrors. So far, most of the literature focuses on the cultural side. So like I said, the link to the goddess Hathor and Ra and all the magical properties and stuff like that. There's not much metallurgical investigation that's been done. Where it has been done is primarily just compositional, whether this is surface analysis or drill samples. It's just what they were made of. However, that's not the full picture. You need how they were made as well. This is where microstructure comes in. Typically, in order to get microstructural information, you do destructive sampling. So you take a chunk of the metal and you mount it, and then that can be analysed. That's also known as a taper section. However, this is very destructive, particularly for mirrors. If you have a whole mirror and you take a wedge out of it, you're going to notice it. Museums don't like that. They're not going to allow you to just take a chunk out of a mirror. So that's where part of my methodology, I've developed a methodology to kind of counteract this. But also part of it is making sure that what is analysed is representative. So part of the Garstein Museum back in the 90s, some of their mirrors were sampled and chunks were taken from the tang. However, when I re-examined the mirrors, the tang was visibly thicker than the disc. This means it was treated differently during manufacture, so the microstructure might not actually be representative of the disc. So again, this is where my methodology comes in, where we're trying to sample from the disc, but for it to be as minimally destructive as possible, while still gaining all of that data that we need to achieve an overall picture. So as you can see, this is kind of what a taper section would do. You don't really want a chunk missing like that. So we've developed what we've called flat edge abrasion. This is actually based from coin studies. They used to do these with coins, but we kind of looked at a mirror and went, oh, that's a similar shape. We can apply it to these. So this is basically where you remove the corrosion layer from the edge of the disc to reveal the bulk metal underneath. So this, you get actual metal, there's no corrosion products interfering with the compositional data, and you can get microstructural data as well. As you can see, so there's this mirror on the left, these two are the same. It's on the left, and this is pre-sampling, and on the right, this is post-sampling. So this is what the actual sampled edge looks like. And you can see visually that's where it's been sampled, and this is where it's been sampled. You can't really tell from a distance, but that has been sampled. One of the limitations of this is if a mirror is so heavily corroded that when it's sampled, there's no metal left towards the surface. So you can't actually gain much more information than the alloy type. But so far, out of about 25 mirrors that I've analysed, only 2 have been this corroded. So I've been lucky in that sense. So once the mirrors have been sampled, they're placed inside the SEM. Luckily, our department's SEM has a very large chamber, which is the only reason I'm allowed to do this kind of work. So the chamber is 200 by 200 millimeters. So all the mirrors I analyse are smaller than this. This means that I can place them as an entire object into the SEM. The sampled edge is then, the stage is tilted, so the sampled edge is then directly underneath the detector, so we can get all of that, all of the data. So if say another department has an SEM, but the chamber isn't big enough or they can't tilt the stage, this methodology isn't really possible. So the types of data I can get from this sampled edge. So this is what it looks like under SEM. It's a grayscale image. So you go from this under just a normal camera to this kind of detail. And then below is an image from the Keynote microscope that we also have in the department. So this is just a color version of this, basically. So far, I've identified 3 different alloy types. So you have arsenical coppers, tin bronzes, and then a ternary alloy, which is arsenical tin bronze. The arsenical coppers and tin bronzes are averaging about 5% of either arsenic or tin. There's a range between about 4 and 6 overall. Some I've seen as low as 2.5%, some as high as 8%, but they're more the anomalies. The arsenical tin bronze, this is primarily where it's about 5% tin and the arsenic is much lower, 1% or less. And this could be due to recycling of earlier arsenical coppers, but they've just added tin later on, because each time you remelt arsenical copper, you lose some of the arsenic. So that might be evidence of recycling. Also, from the polished surface, I can identify inclusions within the bulk metal. So inclusions are impurities that come through the ore from smelting. They don't actually dissolve into the metal. So I've identified 3 different types at the moment. The bright white, which is here, these are primarily lead, with other small quantities of things like nickel, bismuth, antimony. Then there's these grey ones here, which are quite common. They're iron sulfides. Sometimes they have selenium and tellurium in them. These are common for Egyptian metals as they come from the ore, and they were using the same mine for a long time. But they're not always present, but this is probably due to their low quantities, and the limits of detection are not low enough on the SEM to detect them. Then the final one is these black spots here. So these are iron oxides, where iron is about 60–70%, whereas in the sulfide inclusions, it's mainly sulfur with usually about 1/3 less iron. So once all that compositional data has been gathered, I then etch the sample. So this brings out the microstructure. So here, the top one's quite busy. So basically, all of the mirrors so far have been recrystallized granular structures. So, and there's evidence of twin blinds, such as these. So twin blinds show up when the metal has been annealed. This is where it's been worked heavily, it's started to become brittle and it'll crack. But if you anneal it, it relieves that stress, but it stays the same shape. It doesn't melt the metal at all, it doesn't deform it in that sense. It just relieves the stress. And then slip lines, which are kind of these crisscrossy ones all over this sample, they're from stress, so that they're created by extensive hammering and forging. So on all of the samples, I've identified both, which means that the last stage of manufacture was heavy forging, because annealing removes those slip lines. So the final stage would have been hammering before it was then polished to produce that reflection. So part of my work as well is looking at the grain size and trying to figure out how many cycles these mirrors went through. And the smaller the grains, typically the more cycles, the more hammering and annealing the mirrors have been through. So far I've identified grain size as small as 7 microns, but as high as 60 microns. So I'm trying to see if there's any difference in the number of cycles to create that difference in size. What's also possible from my type of sampling is evidence of surface enrichment. So because the sample is a kind of a cross section of the mirror, hopefully, depending on the condition of the mirror, there might be the original surface still present. And part of it, so the enrichment is basically at the moment very high arsenic. I've not identified any enrichment in tin bronzes so far, but that might happen, just haven't come across them. So these are bands of very high arsenic, around 30%. And then here you've still got about 5% arsenic. So 30% arsenic would give you a much more silver colored mirror, a much more silver colored metal compared to 5% arsenic, which is much more yellow in color. So, and you can also identify these enrichment surfaces on the elemental map. So this purple band at the top is basically this whiter metal here. I'm not entirely sure how they formed these layers. As you can see, it's heavily corroded directly underneath, which makes it difficult to see if there's interdendritic feeders, such as on this sample. So some people have suggested cementation is how they produce these silver surfaces. That's where basically they kind of melted arsenic, pure arsenic, onto the surface to create that silver layer, which this kind of microstructure does lend itself to, because like I said, you haven't got the feeders. But on other mirrors, I have evidence of these feeders. So you can see here the white metal comes from the center and goes towards the surface. So this is where the arsenic is kind of squeezed out of the bulk onto the surface. They might have done this just by manipulating the natural segregation of arsenic and copper. Arsenic doesn't like necessarily being in copper. It would rather go to 30% than say 5%. So if you heat it the right way or cast it the right way, you might be able to force that arsenic to the surface to give you that desired silver color. So on top of that, I am doing some experimental work to, like I said, try and figure out how they were creating these surface enrichments, but also to recreate the different compositions I'm seeing and the microstructures, just to how they were doing it. But then this will also link to hardness. So we think the harder the metal, the better the reflection, because the better the polish will take. So were they purposely creating discs that produce the hardest possible metal to get the best reflection? And also how color links to that. Like I said, 5% arsenic and 5% tin are quite yellow, whereas you got the 30%, which is silver. So what were they aiming for, basically? So this is some of the work I've done so far. I've only just started, so I've not got too much to go into, unfortunately. So here at the top, this is called a eutectic. So for arsenic, at 21% in copper is the eutectic. This is the lowest possible melting point for the metal. And it creates this, what I call kind of zebra microstructure. So here the darker, again, is the lower arsenic, and then you've got the brighter, whiter metal, which is the high 30% arsenic. I then diluted it down to 8%. We found dilutions were easier to control the percentage of arsenic than addition. So trying to get to 8% arsenic is very difficult because, like I said, it doesn't like going into copper. By diluting it down once it's kind of already trapped, it's a lot easier to get consistent percentages. So this is just as cast, nothing's been worked, and you can see the dendritic arms. This is where arsenic is squeezed out as it cools. This was then hammered, and this hasn't been annealed yet, so this is just hammering, and it starts to deform those arms. As you can see where I'm hammering it, and obviously it's squishing down, those arms are bending. And then I annealed it, And then once annealed, those arms, although they started to break, they actually started to break, like deform, they started to break apart into what I'm saying is more like islands of high arsenic within the copper. So how does this actually compare to the archaeological record? Am I actually achieving the kind of microstructures I'm seeing? The answer is kind of. It's very difficult to make direct comparisons because obviously the mirrors are thousands of years old, they're heavily corroded. So as you can see, this on the right is a mirror from the Garstang Museum. It's got about 8% arsenic in this bulk area, and then you can see the whiter islands of the 30% arsenic. And then the black bits are just where it's corroded. On the left, this is similar to the sample I just showed you before, except I've done a second cycle of hammering and annealing. So this has been hammered and annealed twice and then hammered again. And it's further broken down those islands of 30% arsenic. And as you can see, ignore the corrosion, it looks quite similar with the islands compared to the archaeological material. So yeah, overall, so far I've identified different alloy types that mirrors were extensively worked, most likely to increase the hardness and to get the desired shape for then a better reflection. And then the percentages of arsenic or tin would have impacted the color of the discs, and it's whether they were trying to get a golden colored or a silver colored mirror, and then how that would have impacted how they viewed themselves. I'd like to thank the following museums for letting me analyze their material as well. Any questions?
Fantastic talk. It's difficult to believe it's only in the first year of your PhD. Does anyone have any questions? Pete, I saw you making copious notes about arsenic whilst Liz was talking.
Well, no, thank you. It's an amazing project, really impressive. What's your thinking on how arsenic in general got into the copper as a process? Because I know there's a lot of thinking of deliberate addition within the Egyptian world that sort of Frederick Rademacher was working on.
Yeah, the percentages I'm seeing is definitely an addition. This wasn't accidental. It is a question of how they were adding it. These kind of percentages probably spice, not just because very early on they probably would have used up the high rich arsenic ores because they would have been like, oh, this melts better, this casts better, and then they run out of it, and then they kind of go, how do we make up for that? So for the percentages I'm seeing, 5% average from the literature, that's quite high in terms of the amount of arsenic. So they're definitely purposely adding it. What I think is a mixture of the hardness and for the color.
Yeah. Would that also be a good intermediate material to crush and sort of for a cementation surface process?
Possibly, yes. That's kind of, I don't know if I'll be able to recreate that because of health and safety. Yeah. But again, that is that could be, that's how you're seeing just that band on the surface. So that could be an easier way of how they were doing it.
So it'd be a fascinating conceptual link between making an alloy, but also decoration and display, and making those two worlds together. It's really exciting.
Is anyone else have any questions? Alan?
Yeah, really exciting work, and well done so far, Matt. How do you see the tin bronze working in relation to the arsenic? There's no evidence of tinning, I assume.
No, not that I've seen so far. I haven't actually, so for Egypt, tin comes in late Middle Kingdom, and then it's the primary alloy in the New Kingdom. There's not as many mirrors that survive from the New Kingdom compared to like the Middle Kingdom and earlier. So a lot of the mirrors I'm analysing are just arsenical coppers. So they could have tinned them. From the mirrors I've had so far, I haven't seen that. And like I said, out of about 25 mirrors, I've probably seen about 4 tin bronzes. That's it. So it's kind of, once I get more mirrors in, I might be able to actually start to compare more how they enrich them and things like that.
Thank you.
Bruce.
Thank you very much for a splendid paper. That was great. You mentioned the corrosion. You have the slide with the corrosion on the right. is there anything that you could do experimentally to kind of get the effects of corrosion without, as it were, requiring hundreds of years? And does the corrosion affect the metal in different ways according to the arsenical content?
Yes, we might be able to artificially produce corrosion. That's kind of later on down the line. And then we're going to kind of see the effects because there's, with arsenic and other metals, there's called solid state diffusion. So this is where the arsenic kind of leaches from high to low. So the islands will start to leach out the arsenic and then the bulk will become higher. This is possibly what we think is happening with the archaeological metal, where originally the bulk might have been lower, say at about 6%, but over time it's been increased to 8% where it's leaching. Also, arsenic actually is more resistant to corrosion than copper. So as you can see on the archaeological material, these islands aren't really corroding, it's everything around it. And also the corrosion is very intergranular. So yeah, depending on, some mirrors are better preserved than others due to the composition. So you got, as you can see around here, that's better preserved than just this lower arsenic here.
Wonderful, thank you.
Liz, slightly left field perhaps. You started off talking about how mirrors are part of the way people look at each other, or look at themselves rather, and they are making themselves up. Mm-hmm. Is there a possibility going on from this? Because obviously you've talked a little bit about how the poor use water, the wealthy use these mirrors, and these mirrors have different colour surfaces. Mm-hmm. Obviously the colours you get back from the surface will depend upon the nature of the surface itself. Does this give us a route into looking at people's makeup and how they change the way in which they see themselves and can see themselves?
Yeah, so part of it, obviously I want to look into colour and recreate the different colours, the different percentages, but also how light impacts that. And yeah, the type of reflection you would have gotten. And then, yeah, how makeup would have looked in that, whether over time, so that's what I also want to see is like geographical and temporal changes, whether, you know, they go from certain percentages to other percentages because they want more of a silver appearance because it would have given you a whiter reflection. So would they have wanted to see a whiter face basically, or a more golden face, things like that. So that's kind of, once I get the kind of the color data for the metals, that's kind of something I can start looking into.
Right, thanks Liz, that was great. A round of applause, please. So before our first break, we'll have one more talk, which is moving into the realm of coinage, which we'll hear more about in several of the later talks. And welcome Naomi Rubinstein, whose presentation will be loading up in just a second. Here we are, Naomi, nearly there. Naomi, take it away.
So I'm going to be talking about the challenge we have identifying contemporary copies in 4th century Romano British coin works. Before I start, it might be just useful to go over the main copper alloy coins of the period. And these are coins minted under Constantine and his sons. So from 330 to 335, the main coins were consisted of 2 city commemoratives. So Urbs Roma, and then Constantinopolis, and then 1 military issue, which is Gloria Exodus with 2 military standards. So these coins contained about 1.5% to 2% silver. And then in 336, the coinage changes and the city commemoratives stop being made. The Gloria coin is reduced in size and one of the military standards is removed. There's also a change in the quality of production, with the 1 standard issues often being of poor quality. And the composition is reduced in silver from the previous 1% to 2% to now just 1% to 1.5%. So what are contemporary copies? A contemporary copy, it can be defined as any coin that circulated alongside official issues but did not originate from an official mint. They could also be any coin It can also be a coin that has been modified from its original state, such as an overstrike in the previous coinage. So we don't actually know why copies were made. We think it might be due to a coinage shortage, but we still aren't really sure. It's not, we don't believe that they're actually forgeries. So they're that weird in between of they're not official issues, but they're not trying to scam anybody. Part of the problem we have with understanding what they are is we don't really know how many copies are out there. So there are two main groups that copies fall into. You have copies of poor quality and often small size, such as the one on the left, no, right? Excuse me. So the one here is so small size, and then you have copies that are actually pretty well made, such as this one, that are often made to really high standard engraving and are often of the correct size for the coins. So both of these are actually to scale to one another, with the copy here being about 11.5 millimeters and this one being 15 in diameter. So it's a lot easier to identify copies and hoards when they look like this, but less so when they start looking like this. So this leads to an identification problem. So currently, copies are identified visually using multiple methods. So this can consist of the engraving style and try to see if the style matches that of known mint styles, or also looking for errors in mint marks and legends. But this introduces a visual bias, given that you're now looking for something to be wrong with the coin, and that might not always be the case, as some copies might not have any identifiable problems. Also, as mentioned earlier, the unstandard issues have a poor quality of production, so that also makes it harder to tell if it's a copy or not based on appearance alone. The addition of corrosion also could hinder identification by covering any marks that might be used for identification. So the issues we have with identifying copies and official issues has led to what has been introduced as a third group. So a lot of museums will start labeling coins as copy, official, and then illegible/unknown, meaning that they can't decide where it falls. But this new third group has led to an interpretation problem. So here's an example of the hoard. Let's say 6% of the hoard had been identified as copies. But it still has 17% that we couldn't really tell if they were copies or not. And this can then be interpreted as somewhere between 6 and 23% might be copies. But that's not really helpful to anybody, because it's very unlikely that all 23% are copies, but it's equally as unlikely that all 17% of the uncertain are regular coins. Some museums have gotten away with this by just removing the entire third group when it comes to interpreting the hoard, but that's not very helpful, and it's pretty misleading, as you're just ignoring the coins that you can't identify. And then this becomes even bigger problem in poorly preserved coins, poorly preserved hoards, where you might have up to half the hoard or up to a third of the hoard that it falls into this new uncertain group. So what actually needs to be done? We need to have a method that can be repeatable and easy to use, but also helps eliminate this need for a third group, because the third group is leading to a lot of problems. So this is where chemical analysis can come in use. So previous work has shown that copies contain less silver than official issues, whereas official issues contain between 1% and 2% silver. Copies contain anywhere from no silver to just under about 0.5%. And because of this, we can use chemical analysis for identification. So chemical analysis helps give more accurate identifications, and it also removes this third group issue. So the downsides of it is often chemical methods can be destructive, and there's been very little work done for the purpose of identifying copies, with the last major work being done in 1976. So One of the non-destructive methods we could use for identification would be X-ray fluorescence or XRF. So it's a non-destructive method, but it's a surface technique, meaning it's only going to read the actual surface of the object. It has the advantage of it's portable, meaning we can bring it into museums and actually carry out analysis in the museum environment instead of needing to take coins out on loan. It's also relatively fast and simple to use, meaning we can go through a large amount of coins in a very short amount of time, which is really helpful given that many of these hoards have upwards of 100 coins. So there are some downsides to XRF. Mainly its low penetration depth, meaning it has inability, it can't really read past corrosion layers. So whatever reading you're getting is just the corroded surface. It also has, with any method, when you normalize the data, you will have an increase in inflation values. But because XRF can't really tell an oxidized metal versus the actual pure metal, you end up with sometimes a higher increase when doing normalization. So because despite the issues with the corrosion, silver is still pretty stable in the corrosion layer. And this actually allows surface analysis to be used to identify copies, given that silver is a defining factor between what is a copy and what is not. So I'm currently using XRF to identify copies in Vermont and British courts. So the first thing I do is I take 6 readings of each coin. So 3 on the reverse and 3 on the obverse, so the front and the back of the coin. And after each reading, I rotate the coin because the machine itself has an 8mm spot size, but the coins are usually between 15 to 20 millimeter diameter. So rotating the coins after each reading helps give a better representation of the entire surface. So then I take so after I have the readings, I then average them together and normalize in terms of the main elements, so copper, silver, tin, lead, and iron. And then I run them through, so then once I have all the data, I start creating the actual composition groups. So one way we can do this is we first look at the data just through principal component analysis. And this allows us to kind of look at all the elements together. And we can see if there is any separation in the data. And we have here a very tight cluster of coins around the center and a very large group kind of off to the side, very spread out. So we then take elements and contribute most to group separation, in this case, tin, and we plot it against silver just to see where the groups split. And here it's showing about 1%, but like I said before, XRF has the issue of inflation when you're normalizing. So it says 1%, it's not actually 1% compositionally. But then we take this groups that we've just made and we apply it back onto the actual data set. We end up with 2 separate groups. So we have the groups with low silver and the group with higher silver. And we're labeling lower silver ones as copies and the other ones as official issues. So how can we test that this is better than that this actually works? Well, one way we can test the method is comparing the chemical groups to random sorting. So we can use discriminant analysis as a way of doing this. So if the hoard has 470 coins, and we're saying that 51 of these coins are copies, if there is no difference between copies and regular issues chemically, then just based on the size alone, we would expect about 1.2% of the coins to fall into the correct group for copies. So about 6 coins out of 51, which is pretty crap. But if you look at the actual composition groups, we end up with 43 out of the 51 classifying correctly. So this shows that there is a clear difference compositionally. So the chemical groups are valid. So the second method we use for validation will be microwave plasma. And this is, so to do this, we take drill samples for about 8 to 10 coins per hoard. And we run them from coins with low silver all the way to the coins with higher silver. And this kind of helps us look at the scatter plot and say, are these our data points in the right spots? This method gives a very accurate composition from the core samples. So you end up with, as you can see here, we're taking about 10 milligrams from each coin. So it is destructive, but it's minimally destructive. So there are some limitations to using XRF for surface, using XRF for identification. Currently, we still do need a small amount of destructive sampling to make sure our data points are in the right spots. And we do need comparison with other coins from the same environment and burial to make the identification. So we can't just use this method on random site finds. Also, the burial environment may have an effect on the classification, whereas the group separations might be very clear in, let's say, acidic hoards. In really well-preserved hoards, that might not be the case, as corrosion would have had different effects in the coins. And so that needs to be kept in mind is not all copies might have low silver. Some copies might be made from remelted previous coins, and therefore they would read high silver. And also some copies might be made as an overstrike. So they would take another coin and strike a new picture on it. So how can we actually use this? So one of the hoards I've analyzed, the pool hoard, originally had 37 coins out of 470 identified as copies. With XRF, we were able to get 16 new identifications, giving a total of 53 copies, 2 labeled as copies due to being overstruck from another coin, and the rest being found as chemical copies. So once we start being able to get a better understanding of how many copies are in a hoard, we can actually start building up distribution patterns and trying to understand, is there a difference between copies in the hoard and the regular coins? So as you can see here, in the regular coinage, about 51% of them are of the Gloria exertis type, and the others are split between Urbs Roma and Constantinopolis. When we compare that to the copies, that's not the case. We can see that 30% of the coins are actually of the Urbs Roma, which is a lot more than the 23% in the regular issues. And we can see here that in this hoard, copies are more likely to be of one of the commemorative types than they are of the other. So the reason for this is still not known, but we can start using these distribution patterns in other hoards to try figuring out, is this pattern something that stays the same in other hoards, or are different hoards more likely to have different types of copies? So in the future, we can hope that this method will allow chemical identifications to be carried out at the same time as traditional ones, and it opens up possibilities for reevaluating past hoards. And once we start doing all that, we can start piecing together regional maps and distribution, trying to figure out which areas have more of what type of copy and where these coins are coming from. So, currently identifying these coins is problematic, but this method offers like a good chance for improvement, as well as being widely accessible, meaning it has the possibility to actually be taken up by other museums and let them start carrying out their identifications. And once we start doing all this, we can start building up these regional patterns that will allow us to start answering questions about where the coins are coming from and maybe what their actual purpose is. Any questions?
Thanks, Naomi. Well, do we have any questions for you?
Yeah.
Again, this is really exciting work. In terms of the copies, can you, if you got to the stage where you can compare the composition of those coins with sort of wider other types of objects, are they more similar to domestic metallurgy, or are they fresh made from scrap, or can you work out how that metal was accumulated?
So the microwave plasticity we've done on the copies, it seems to be the metal is actually very pure. So it's likely that it's being made, they're being made from recycled metal that's been heavily recycled in the past. So they're not just rebuilding old coins and making more coins. They're taking pretty heavily recycled metal and starting from there.
A sort of couple of questions on the sort of context. Do you get these contemporary copies before 330, and do you get them? I think you mentioned at the start that that's Romano British coinage. Do you get them elsewhere in the West?
So they seem to be pretty much unique to Britain and parts of Gaul near the coast. They don't seem to be showing up anywhere else in the empire.
Right.
They don't seem to be. There are other types of copies in earlier coins, but these ones really just start in 330.
I mean, I wonder if one sort of thought might be that you have a lot of kind of turbulence in the period, at least up to 324, and that maybe you've got sort of coins from, with emperors who you don't particularly want to see around on your coinage, and I wonder if that could be sort of behind it.
I mean, it's a bit weird when you look at the types of copies where you have more of them on commemorative issues, which don't have any emperors on the obverse. Instead, they just have like Romo, which is the personification goddess of Rome, and you have Constantinopolis, which is the personification of the city. So there might be a bias on who they want on the coins, but we don't really.
But it's really intriguing, but it's excellent with what you're doing with it.
I was interested when you said you wouldn't consider them forgeries or an effort to deceive. So what role would they have played, and who would have been issuing?
We don't think they're forgeries because they seem to be hoarded pretty frequently with normal coins, and they're found with normal issues and site finds as well. So they're clearly being used as part of the coinage system. We don't really know where they're coming from, but it's probably local manufacture in different regions. And it could be a response to the fact that there was no mint in Britain during this time, because it had closed a few years earlier.
So they were certainly accepted.
Yes, it seems to be, they seem to be accepted as coins, and people were using them as coins, even though they were not produced at actual official mints.
Well, does anyone have any more questions? Thank you, Naomi, for a fantastic talk, and thanks for everyone for the first part of the conference. There's some coffee and things. We'll take a pause for maybe 15 or 20 minutes, and then we'll return for our keynote speech. Thanks very much, everyone. Thanks, Naomi. So. Right. Well, good for everyone. I think everyone's back in. Well, welcome back. We are now. I'm very pleased to welcome Dr. Peter Bray from the University of Reading, who has had the great privilege of working with me for some years now. So Peter began his work on the study of metal. Well, he finished a PhD in 2009. Is that right? Something like that. Yeah. And has been working on the questions to do with the way in which we can approach archaeometallurgy en masse, thinking about really big scale questions about exchange and communication, thinking about the way in which we can bring those kind of archaeometallurgical studies to really understand human questions about the way in which people were using metal and relating it and fitting it into their lives. He's going to give for us today a pretty broad and exciting title. We should analyze everything. The pragmatic and prosopographical. I can never say it. Try it again. I have to loosen the mask for prosopography. So the pragmatic and prosopographical case for archaeometallurgy in the UK today. Peter, take it away.
Thank you very much, and thank you for the invitation to join you today. I think Liverpool is doing remarkable things on archaeological materials, and it's a real guide for what I hope we can build at Reading. So it's fantastic to be back. So this is a title, a cleaned up version of what Peter suggested I talk about, mostly because he knows I can't pronounce the 6-syllable word in the middle. But I think, believe it or not, it is actually a useful model for how we might be able to take things forward. So there are some signs of promise for the field out there. That can't be denied. We've got exciting, unexpected injections of cash, which was from the HRC with their recent CAPCO fund, and we know that that's going to be extended and repeated. So that's a wonderful addition to infrastructure, and we've been lucky at Reading to get a machine that will be very familiar to everyone in this room, so an MPAES of our own. However, we can't deny that the archaeological science of materials is under tremendous pressure from almost every angle. So, I mean, this is a quote from 10, 11, 12 years ago, saying that the sector is fragmented, undervalued, and recommended we come together to develop national strategies and investments and planning. And with the awful things that are happening at Sheffield now, we know that no matter what the great ambition is, in practical terms, our field is unfortunately under threat. So today I want to focus on a number of related topics, mostly on copper alloys, I completely admit, about what chemistry can do and why we should be confident and why we should expand. And ultimately, yes, we should analyse everything, but that may take some time. So there's a definite opinion that there's too much chemistry already, which I find kind of bizarre, but I am slightly biased. So a discussion 5 years ago now, a noted theorist, who I'll let remain anonymous for now, said we have too much chemistry. And what he meant was the chemical work on materials is diverting us from more interesting social questions of craft and identity and value and personhood and so on. But I think that's a chemical question as well. Us as scientists rigorously can look at exciting social questions, and I'll get onto that in a minute. But there's an underlying concern, and there has been for decades now, that there isn't enough chemistry. And one of the reasons for that, as Paul Craddock argued in the mid-80s, was that chemistry was seen as only good for provenance. It was only good at where this stuff came from, or simple ideas of process. So therefore, as soon as things get really complicated, analysis can't help because things are already too complicated. That not getting a provenance is a failure. Therefore, let's not invest vast amounts in analysing things because it's too daunting, is the word that Paul used there. And conflating those two, I think we need more data in order to take on those big challenges, that we can look at social questions, we can look at recycling, we can look at really nuanced, interesting processes by applying chemical analysis. And I know I'm definitely talking to the choir here, but I hope to lay out that argument in more detail. So what are the positive reasons to expand and be ambitious about chemical analysis within archaeology departments today, when it is seen as expensive and it is seen as difficult? And sometimes that is true. I think this is Bruno Latour, it is most profound. The conceptual reasons: we can have a great social impact. There are new and exciting, interesting chemical approaches, and we've already seen those today. And we can blend with exciting stuff happening in the digital humanities, and taken all together as a package, what the chemical analysis of copper alloys, which has been happening for 200 years, can still contribute to new and exciting, better archaeology, and may even attract, hopefully, large amounts of funding. So in terms of chemical arguments, we even after all those hundreds of years of research, we still have to argue, what does chemical data of artifacts represent? And my whole research career has been about broadening out that question. Provenance is still in there, absolutely, but can we talk about a wider characterization hypothesis instead of just the provenance hypothesis? Can we, I mean, it's not catchy, it's a bit wordy, but can we chemically identify events and processes within the entire sequence of a unit of metal's life, from its origin to its final deposition, everything in between, including mergers and complexity and nuance? And having achieved that, can we properly line that up with other archaeological data sets? And I think we absolutely can, but it does take a lot of data and new thinking. So the old provenance hypothesis was often built on a trust that there were deep patterns in geochemistry, and there were consistent patterns in geochemistry. So a great deal of the huge analytical projects in the 60s were based upon ideas that there were repeated distributions and fundamental laws of geochemistry. And that allowed the application of quite straightforward statistical techniques to identify groups, which then could be linked to source, and the world would be connected. There was great variety and local patterns within geochemical sources, and therefore even if we are engaging with that most prime data, we have to allow for variation, and we have to embrace variation and make use of it. And these two authors really support the use of what's often defined as simple approaches, just straightforward data analysis or characterization in order just to gauge what that variety is telling us. And obviously, as archaeologists, as we take those characterization tools forward, we move from geochemistry to people, but we can hopefully link that whole sequence together. So what I argue for is not absolute chemistry in the sense of absolute dating, where a scientific process can tell you how old something is directly by various deductions and inferences. I think we need to look at a relative chemistry and just accept that that's the world as it is, but that's an exciting, complex social world. We need to look at the combinations and levels of various diagnostic elements. We need to look at context. We need to look at different processes to explain how those elements either focus or spread out or get mixed or don't get mixed, get depleted or get enriched. And if we do that carefully with a lot of data, we can see very interesting processes on a variety of scales. So I'm very interested in the affordance of technology, but in the sense of what do our scientific techniques afford us? What do different ways of chemically analyzing things, how does that open up or constrain our thoughts? But anyway, so we have the affordance of the source in terms of its chemical composition, which, as recent work has shown, may be often extremely varied. And then that may or may not undergo different processes of dilution, of recycling, maybe none at all, and we have a direct deposit from relatively prime metal. But we need to see it in context. We need to be rigorous scientists and, rigorous archaeologists. So a very, very quick example. And the European Bronze Age is the densest data set we have. It's the most thought through data set we have. And it's kind of the best example, but it is a small part of the world for a short amount of time. But we have a number of proven European Bronze Age mining sites, often by absolute dating and superb excavation. We have a huge number of analyses, relatively speaking. So the dark red dots there are over 500, around 500 analyses just for that area, but just by one project, the SAM project from Stuttgart, which lasted for a number of years and built and built and built. There's a lot of empty patches there, but when they analysed, they really analysed. And then we can look at focuses of different compositions within all that huge amount of data. So this is, the red dots here are where there's a lot of arsenic within the copper as the only other element there. And you can see there's a real focus there in Iberia. Blue is where there's almost no arsenical copper of that type at this time, which is the early Bronze Age 1. And then there's some orange and yellow in the middle. So just on the presence-absence scale, we can see real focuses of chemistry on an international scale, which links up quite well with what we understand about Iberian mining. So that's not a great jump forward. But if we start to look at the variation of chemistry within that overview of a map, we can start to see variation and change which moves through space. So, I mean, as has already been mentioned today, the idea that arsenic is not stable, it likes to oxidize, it likes to be lost out of copper, it can be a great tool for us. So in Iberia, where we also have a lot of it anyway, the arsenical levels can be extremely high. There's outliers up to 12%, that's probably surface effects. But then the main sequence is clustering around 1.8 up to 2%. So the argument, but as you look at very similar metal, there are these sequential changes into Western France, into Southern Britain, into Denmark. And if we link the overall distribution with the typology, with the mining archaeology, with the sites, and with the real context, we can see a series of interactions where this metal isn't going directly from source to deposition. We see it's been used, it's been reused, and it's been reimagined as objects, not ingots, but objects from Iberia, move into Western France, get remelted into local types. So some arsenic is lost, which preserves that connection, and then further sequences of that active flow it goes on into Denmark, where the arsenic levels are highly suppressed. And most of those regions aren't producing copper. This isn't a series of mines that luckily produced a step change in arsenic content. This is one major production region of this type, which is then used and reused and reimagined. And this works on a huge continental scale, but we could, my PhD was applying this from the Republic of Ireland and Britain on quite a local scale. And we can also look within objects in the same idea of combination technology, where we see the rivets and the blade and how there's reuse and repair and kind of complexity there. So the chemistry here is trying to be active, but it's trying to be relative. And we need a lot more of it, because the early Bronze Age is a massive exception. And we need huge amounts of more data in other periods to untap that potential, basically. And if we move on to social impact of how chemistry can help, I know absolutely Liverpool and most departments do obviously engage with the new archaeological record. But can we work out a way to make that systematic in the same way that radiocarbon is the everyday tool now, even within units? How does material science achieve that? How do we become just another part of the regular process? So the money is tight. We have to come up with new ways to sell this so that can be passed on to developers, that this is a value added, that this can really help. And obviously we have the Portable Antiquities Scheme, which has been a remarkable success. It's engaging with new communities of people. The sheer volume of material is changing the record, and there's new regional coverage and widening of what's coming out of the ground. And again, how do we even begin to tap that insanely large amount of material? And working with the Society for Museum Archaeology, I mean, you hear terrible stories, hopefully from the past, where we take people, the community takes samples, produce their numbers, but then there isn't that engagement back to tell stories and help redisplay and help engage people. As scientists, we need to be confident that we can engage and tell human stories in order to keep those collaborations going and build and build and build. But that often isn't happening. So in terms of, I mean, I'm sure everyone's familiar with this, but just it still shocks me how much metal is coming out of the ground now, which is almost chemically mute. It's almost untouched by modern analytical science. And so this is Emma Durham's work at Reading about known metal figurines. This is already, I mean, remarkable work, but this is already kind of out of date because of the PAS. And this is just Roman coins recorded in the first 13 years of the scheme. This is more than doubled since, and I'm sure everyone's familiar with that. But the numbers are staggering, and the potential is staggering. So this is obviously already up to 1 million as soon as the glut from the lockdown gets processed. So we were talking about 1 million objects, broadly speaking. Half of all the objects found by the PAS is copper alloy, and a third of everything found by the PAS is Roman copper alloy, and probably therefore about 20% of everything from the entire PAS is a Roman copper alloy coin. And copper alloy and the Romans are a real outlier for what this new archaeological record looks like. And in chemical terms of what has been processed to the highest quality, the quality that Matthew's producing, it's a fraction of what exists for early Bronze Age Europe, despite the vast difference in the absolute levels of metal that's employed. Conceptually as well, I think us as scientists need to be stronger about our models. They're not, our scientific models are conceptual models, and we are using a different type of archaeological data to imagine these past worlds. And what strikes me looking at the traditional sequence is that this book was so influential, so impactful, but the ideas have been around for hundreds and hundreds of years. So one of my favorite theorist is Walter Benjamin. So in The Task of the Translator in the 1920s, he was saying that the idea of life and afterlife in works of art should be regarded with an entirely unmetaphorical objectivity. Even in times of narrowly prejudiced thought, there was an inkling that life was not limited to organic corporeality. There's about 1 million words I can't pronounce in this, but it cannot be a matter of extending its dominion under the feeble scepter of the soul, as Fechner tried to do. Silly Fechner. Or conversely, of basing its definition on the even less conclusive factors of animality. I hope you can fill in the gaps, such as sensation which characterizes life only occasionally. And the concept of life is given its due only if everything has a history of its own, not merely the setting for history, but the landscape archaeologists will have an argument with that, is credited with life. And nothing's new under the sun. But this recent trend towards anthropology driving our conception of object biographies or object agency needs to be put into this deeper concept. I mean, I'm not arguing we should go back to silly old Fechner with his Gaia hypothesis in 1851, but what we can do is talk to other communities grappling with object agency or agency in general and work out how archaeological science may have a more natural fit. So the work of Laura Pearce at the Pitt Rivers and Chris Gosden and kicking off another round of interest in the agency of objects can't be underplayed. That's a tremendous achievement, and it is still the dominating theme within most of the Bronze Age communities I engage with. But we can't get around the fact that we can't have this richness of data, this thickness of data as archaeologists. And I mean, it still comes back to those fundamental data issues. So the closest we've got in terms of recreating an anthropological style biography for any object probably is the Gundestrup cauldron. So the largest known silver Iron Age object with this remarkable art style and obviously volumes and volumes have been written about this object, obviously. But the scientists have also thrown the book at it. I mean, we've got everything here. We've got lead isotope analysis, the flow of raw materials, black substances, accelerated dating, a history of scientific research before all these people came together. And even under all that expense and focus on one of the most evocative, exciting archaeological objects, we still can't write an anthropological style biography. It's just a natural limit to what we can achieve. And that's not a failure, that's just our data, that's our reality. So what can we offer that's positive and to move forward? We can look at how clustered our science is. We can argue about how all these different techniques I've listed on the left there tell us different things. What does chemical composition say? What does metallography say? What do hardness values? Lead isotope analysis, absolute dates, whether all of these are fragments of biography, particularly when put alongside context and typology and all the other archaeological approaches. What surprised me was even under the ideal conditions of the early Bronze Age, all this data is British early Bronze Age science, things are highly, highly clustered. We don't have much depth on any Bronze Age objects from Britain naturally, if you see what I mean. If we claimed, which I don't think we can, if we claimed that all of those techniques applied to one object would allow us a scientific biography, even if we claim that, which I don't believe, but even if we claim that, that happens on no object. And it's too expensive and it's just not feasible to do. I mean, we really can't. And if we look at how many couples of techniques we've applied, they tend to cluster very highly. So if you do metallography, you need to know the composition in order to understand the process that metallography is revealing. But if you have metallography from a Bronze Age axe, only 4% of those will also have a lead isotope value. And the expense of bringing all those numbers up to 100% is impossible. So this is where prosopography could come in. It's a very exciting idea in the digital humanities, which predates digital. I mean, there are great volumes of prosopography for the Byzantine period, for the early Anglo-Saxon period. And I'll try and explain what it is in a nutshell. So it doesn't help itself. I mean, in terms of, it comes from the rhetorical term prosopoia, which I'm sure we're all very familiar with, which is the idea of evoking an imagined or absent person through your rhetoric. But the principles are really, really simple. It's just got a very, to me as an archaeologist, I've never come across it before till it hit me about 10 years ago. So the principles are very simple. It's a research approach rather than a method. It's just an attempt to bring together all relevant biographical data of groups of people in a systematic and stereotypical way. And by stereotypical, they mean a standard questionnaire, a repeatable approach. And it's a system for organizing very scarce data in a way that by bringing it together cleverly, it acquires additional significance. It reveals connections of patterns and historical processes that otherwise would have been missed. And a great example of that, which I encourage you to look at, it's a great achievement, is the prosopography of Anglo-Saxon England, where it's a database of gleaning as much as they possibly can from the scarce record. So you've got chronicles, saints' lives, charters, inscriptions, the Doomsday Book, obviously, coins, and it scrapes together sometimes proto-biography of kings. And then you've got 877 named bishops with the land they're giving out and the retainers they're paying off and so on. But then you have 10,000 anonymous people that don't naturally fit into a written biography. How do you write that where all we know about this person, we don't even know their name, but we know that 100 people paid taxes from this particular village to this particular feudal lord, or whatever that connection was. And this strikes me as what we can do as archaeological scientists. This strikes me that this is a positive way forward. We're still engaging with biography, but it's linked to the scarcity and complexity and challenge of our data. But sometimes we can do the Gundus-Rutgolden approach, which is parallel to the King Edgars of the world. The bishops are like the iconic hordes where we can cluster data and cluster context, and it has power to reach and bring the record together. But there are a lot of draws upon draw upon draw upon draw of anonymous objects cut off from, they weren't scientifically excavated, or they are relatively mundane, or they're relatively undiagnostic. But by chemically analyzing them, applying some ideas of these new models of chemical flow and change and contact and the ideas we've seen earlier today, we can breathe some life into them, and they can be brought together in interesting ways so that the sum of the parts is much greater. And there's a lot of digital humanities work going on about how this is done, but none of it's on material culture. It's all on people. So the conceptual leap to say that metallography is in some way related to passing the lives of the Anglo-Saxon saints, if we can persuade people that that is some kind of conceptual link, there is meaning in that, we can hopefully move forward. And I think prosopography, with its silly name, is just a metaphor or just a name for good archaeology, just thorough, lined up, data mined archaeology. And there's other remarkable achievements that, again, have great archaeological theory impact. So CDOC CRM is it's so hard to get excited about. It's so tedious. It's a rigorous model for how you preserve museum collections and other heritage collections, but the intellectual imagination of how they've created this living framework that can capture any heritage information is remarkable. And again, it feels more real to me about how we could move forward in terms of object agency and active people in the past doing technology, but it's seen as a reference model for museums, but it's actually theoretically extremely rich for what we want to do as archaeological scientists. So that's my sales pitch. And all of that has been written into various funding applications. So within Reading, what I'm trying to push is how can I justify analysing a huge amount of Roman and early medieval copper alloy? And my feeling is that it's extremely challenging to go in and say, I want to analyse 10,000 things. But I think from the various perspectives that I've tried to highlight, I'm sure you've got much better examples of how we can impact socially and we can work with digital humanities and so on. I'm sure there's stronger case studies, but I think that across a range of artifact classes, across the entire UK, that level of data analysis is a minimum, really. I mean, even if we achieve 10,000 analyses within one lab over 7 years, we're still less than 1% of the whole record. But I think it would move things on dramatically for how we look at the Roman economy, particularly if we align the remarkable achievements for silver and copper alloy here with a range of ongoing projects. So to do it, I'm trying to work with as many different organizations as possible, from universities, government labs, heritage charities, national museums, and the huge impact, hopefully, from the Portable Antiquities Scheme and the commercial units. So this is the medium to long-term aim. And the conclusion is that the rigorous study of archaeological materials has to draw upon everything now. It's every facet of modern archaeology is in there somewhere. And what's particularly strong and particularly great about archaeological science is that we have to collaborate beyond archaeology. We're always in chemistry, we're always in geography, we're always in these other disciplines. And I know that is very true for almost every archaeologist nowadays, obviously. But the sharing of resources, the sharing of ideas is very strong for archaeological science. And I think, therefore, we need to be confident about what we can feed back into other areas of archaeology that are seen as the preserve of other thinkers. I think we do have a lot to say about the theory of archaeology, about engaging with anthropologically based ideas of material culture. I think we can not say we're right, they're wrong, but we can absolutely have a very productive dialogue when sometimes the numbers get in between us and it stops those conversations happening. When people say, well, I don't do science. It's, well, no, but the thinking, the ideas, surely we can come together quite productively. And the naive hope is that we should try to expand. We can't just hold on to posts or hold on to courses or hold on to facilities as they're slowly eroded. Expansion and being ambitious about what we can achieve is probably the only way. But thank you. But I know I'm speaking to the converted. And so thank you very much again for my warm welcome today. Thank you.
Peter, thanks very much. That was a really inspiring talk to think about. And even though sort of having worked alongside you for many years, thinking about some of the way in which you can approach this material, it's always quite sort of a boost to hear them expressed again so eloquently. So, does anyone have any questions? Oh, has Pete stunned you? Matthew, please.
I've got a complaint. Why am I not on that list?
Oh, sorry.
What was the question? That's excellent. Does anyone else want to have any questions? If not, I have a sort of a question for discussion. Really, it's something thinking about the way this sort of presenting this study of metals in this way as prosopography is, I think, it feels. I know personally, I've always found it to be something which is quite sort of difficult to engage with. Perhaps it's just because it's a word I can't say. But as I'm beginning to think about this, thinking about different types of materials, as you said, it's something about the way in which it feels like good archaeology. And I wonder those who have more experience of looking at other materials like stone and things might think about whether actually this is something which is not explicitly explored in this way, but whether this is an approach which actually has a lot of familiarity, thinking about the way you reconstruct technological sequences, connections and communication between not only at sort of big scales, but also in terms of sequences, thinking about use of individual objects, thinking about those structured patterns which emerge out of large volumes of otherwise apparently disconnected lithic material, whether there's actually a model for that which might kind of fit together, and whether there might be ways in which to connect them together as well. It's something which occurred to me as we were thinking of this. I don't know whether you think that's a valid sort of thing to explore, but
yeah, I think one of the advantages of thinking in that way is exactly to align different materials, and it gives us a ready way for composite materials and difficult things that don't fit neatly into one box or the other. So one worry is that unless we're prepared to have very complex interrelational databases of everything, we will constantly go back to the same linear thinking, and we'll do what's appropriate for each different material or each different technique. The reason that rather than just trying to be good archaeologists, but actually embracing what's been achieved within this prosopographical field, or coming up with a better name for it, is because they've done the heavy lifting on how to build those databases, how to see those links, how to bring incredibly complicated site-based analysis together or diffuse museum collections together. The CDOC CRM and the King's Digital Humanities have achieved amazing things that hopefully we don't have to start from the ground up. All that heavy lifting has been done to some extent, and then we come in and add another layer of complexity in terms of process and active material culture. So it just, I mean, even in all the extremely eloquent and interesting papers on biography, there were like Jody Joy work on mirrors. He always is making parallels. He's always borrowing ideas from the wider Iron Age material culture to get to make the biography argument. And he says, well, of course, biography isn't linear. It can be fractured. You have to sometimes borrow from the wider pool of metal in order to support his argument about a particular composition and so on. That's prosopography, really. But if we also bring in the wider context for late Iron Age life, it becomes richer and richer and richer. And as we move towards the national collection, as museums digitize, as museums link, now's the time to really inject all the stuff that's deposited with the ADS, all the private collections of data, and link now, otherwise we'll lose that opportunity. And this is a nice conceptual way of pushing why it's important. It's not a very pragmatic way because it's a terrible name, but it is an interesting.
It isn't part of the problem a historical one in terms of the way archaeology and archaeological science have been done and have perceived to be done by different practitioners over the last 30 years or so. There is something of a silo mentality, I think, going on here. And this has not been helped, of course, by the fact that traditionally analyses of all sorts have been considered an expensive luxury. So going back to your plea, which I heartily agree with, and we talked about this before, of course, the idea of chemical analysis being a routine part of a post-excavation process, which of course was what Justine Bailey tried to do back in the 70s with the Ancient Monuments Laboratory, where material was going through the labs for conservation and basic cataloguing, and she took the opportunity to do what by today's standards is a very sort of rough and dirty XRF analysis, but it was a way of getting some analyses done on a routine basis. And I think what we're talking about here is very much of the time analytically, because we have analytical techniques that are relatively inexpensive, that are very reliable, that can be done very, very quickly. So we can get a level of data now, which was hitherto not possible, really quite cheaply. And I remember sitting at a meeting, a lunchtime seminar, over in the old Hartley building a few years ago, and they had somebody talking about investigation of chromations, I think, and the use of isotopes. And I can't remember who gave the paper. It was very interesting, but the person I was sitting next to at some point came out, oh, can't they just give us the answer?
Yeah.
This exasperation with the scientists who have always, unfortunately, held themselves up as being the people who present the answer because it's science, wasn't able to do so. And my archaeological colleagues sitting next to me was getting very frustrated with this. And I think that archaeological science did itself a great disservice by offering to give the world, to give the answer, and singularly failed to deliver repeatedly at a considerable expense to an archaeological budget.
Yeah.
I think now things can move on. And I think what you're proposing here is definitely the way forward. But I think there's going to be a lot of convincing that will need to be done because of some deeply held biases in certain quarters.
I completely agree. I mean, in a sense, a mass analysis program now, and that's what I'm trying to justify, is doomed to fail from two quarters. One, because we will never be able to approach a modern anthropological view of active material culture in bio. I mean, I know people are already moving beyond that, obviously, but that kind of feeling of that richness, that what we propose is sometimes looks very different to that. And as you say, we also are moving away from chemistry alone as being a provenance tool. Therefore, we're doomed to fail, because our raison d'etre used to be to promise where something came from. And what we're now seeing is complexity and change and process that's hard to bound sometimes and is diffuse. So yeah, so what I'm absolutely, I mean, there's just so many ways we can give back, but how we make it into a punchy, saleable package, when what I'm really arguing for is for archaeological science to be a rigorous just archaeologist, just part of a much bigger conversation, where we're not in the microfiche anymore as an add-on that, as you say, will tell some independent truth that can then be interpreted elsewhere. How do we become part of a wider conversation is really challenging. And I think in terms of the capacity for cheap, almost lightly invasive research is absolutely there. And we can learn a great deal from when the last time that was feasible, which was in the 60s. It's amazing how much of that huge amount of data has been dumped and ignored. When it's full of richness. And that's a really strong argument for chemistry that I didn't come onto is how, because we're looking at repeated elements in a set diagnostic set, we're looking for 16 things, but we're looking for 16 things in China, we're looking for 16 things in North America, and everywhere in between. It can really pull the world together very quickly. And that is a power that some other archaeological techniques don't have, and we need to make more of that.
Very good talk. We really enjoyed that. So I think the strength of the archaeological community being linked together is really important with Reheating and the other centres and the cheap analysis, etc. But funding obviously is the key to that, and capturing the public imagination is central to that. Even if there's like headline stories that capture the imagination where there's all the complexities behind it. I mean, I'm thinking of the Nabra Sky Disc, which absolutely huge amounts of money were thrown at over 5 years or more. And it's that sort of, there's all sorts of issues related to that, but capturing the public imagination in those sorts of ways would be a great help in getting the funding. And maybe we need to focus in on a few objects to get that interest and help the funding along.
I absolutely understand what you mean. I mean, I don't agree, I'm afraid, which is I don't like the iconic object way in. I completely appreciate that eyeballs are important and impact is important, and the easiest way is to do that. I understand completely. Is there a third of all the money that I put into this multi-million pounds application is on training and engagement and other ways in. And I know I'm very naive, but I still hope that telling exciting, impactful stories about the everyday could be more meaningful to people than something so extraordinary and so alien, or so extreme as some of these, amazing.
I agree entirely.
There's a room for both.
Making the everyday more interesting.
Yeah, I'm sure that there's definitely a happy middle. I'm just with the huge controversy about so many of these foundational objects. Sometimes the disagreement about the tin isotopes within the lead sky disk can then seem like we don't know what we're talking about again. But the wider debate about what we can do for all of archaeology.
So I suppose the broader point is making it more accessible and interesting.
Yeah.
To a wider public.
Oh, absolutely.
And without getting hung up on the detail of it, which we can discuss ourselves. But it's the way we present the things that we want to promote.
Yeah, of course, absolutely, without doubt. And I think radiocarbon has achieved amazing things. It's like, how has such a complex physical process become everyday? And there's huge amounts of training schemes going on for people from units or museums or universities to engage with that technique. And now it's a trusted everyday tool. And Bayesian analysis and calibration, all these things, that these are complex, difficult things that have somehow become accepted. And if we achieve that within the archaeological community for what we do, then the human stories will become more abundant and we can sell better. I mean, I completely accept that the Nebris Guidis and the Sun Chariot and the Gunship Cauldron can be the tip of the spear, but I hope there is something more social and fundamental to back it up.
I mean, the other thing I've noticed is the ancient DNA are using maps of material culture movement to back up what they're saying. So we can add to those stories in a meaningful way.
Yeah, absolutely. So, I mean, Barry Cunliffe at a conference stood up. So I'd just done my piece on material culture, and then a DNA specialist spoke, and then Barry's keynote was, as we can clearly see, DNA is the future. It's like, cheers, Barry. But integrating the two, absolutely. How do we draw together these very different concepts? And that's where a framework, some kinds of just biographical framework, or some way that links complex data rigorously, can help those arguments, rather than, because otherwise we'll end up with a cherry picking of results rather than the data leading the discussion.
So two more quick questions, Naomi.
More of a second observation. I'm thinking from a museum perspective, it might be useful to get people more aware of the fact that metal isn't as long lasting as people seem to think it is, and that after excavation, there is a chance that we will lose the object. Because right now people say, oh, we can look at it later. And I've been on the other end where I went to find an object in a store that hadn't been looked at since 2005, only to find out that it had been completely destroyed by bronze disease in between then. And the object was lost, and we had no analysis or anything done on it.
Well, that's an excellent point. I mean, the amount of metal leaving the ground now is now its most vulnerable point since it was deposited. Absolutely.
People's perspective changes, saying, oh, we can look at this later too. We might not have a chance to do this later.
Yeah.
Then we get more people willing to say, actually, this is needed because we might not have another chance.
Yeah, it's an excellent point. I mean, the conservation scientists looking at that may go, well, we're working on the wrong crisis, the crisis to make sure there is something in the future. That's an excellent point.
Bruce, did you have a comment?
Thank you very much indeed. Very exciting. I mean, one thought is that one approach as regards the funders is to stress the kind of the big data angle, because they're often, this is seen as a kind of virtue in its own right. And I think pointing out that the science will give us this. I mean, what you said, for example, about if there are 10,000 copper objects in sort of Roman Britain. I mean, this is incredible. And I think that's the angle that we should kind of be taking in our departments, that actually doing the science will produce the kinds of insight which, say, people who had to think about the ancient economy purely from inscriptions say, that's only part of the picture. I mean, they're very nice inscriptions, they're texts, and don't get me wrong, I mean, I'm somebody who works on text, but if we can make the point to our funders and if you like, our kind of institutional masters, that if this kind of level of data is going to be transformative, that must be the way, I think.
Yeah, I think, I mean, thank you, that's a great point. I think the level of data at which it becomes transformative is for chemistry surprisingly high. And it comes back to what Matthew was saying about in the past, one analysis represented an object class and a place and a time. And I think as we realize how complex the chemistry is, all of that becomes to appear at quite a rich data level. And I find myself currently hiding my data analysis under other things in order to do the big data. I'm pushing these other angles that I've kind of discussed part of today. And I'm thinking of going to Europe, and I've been told there's no chance of placing a major chemical campaign at the center because it will be seen as repetitious in some way, or you're doing a large thing by doing a small thing 100,000 times. And it is transformative. It does bring in change, and it's trying to persuade people of that. So the way I'm probably going to sell that is the data digital humanities angle and that unlocking power. But we have to persuade the funders, but then also persuading our colleagues that we're worth investing on that micro level, because even if the objects are corroding, that data can still accumulate and we can put stuff together. I mean, I had a wonderful insight thanks to something Matthew did many years ago, because those numbers work and it fits and it brings something together. So all data is useful, even if it initially doesn't work.
Thank you. Peter, that's fantastic. Thanks again for a fantastic talk. So we now return to our Liverpool contributions to the conference. I'm just going to load up, I believe, Matthew, you're now up next. So I'll invite you to stage. Dr. Matthew Ponting, who is the Senior Lecturer in Archaeomaterials at the University of Liverpool, is now going to present to us again, returning to the issue of copies. There it is, I've got it. Okay, so let me hand over to you. Okay.
Thank you very much. I first want to correct an omission from my earlier introduction, which was to thank Peter for organising this. I was going to, and then I don't know, it slipped my mind. Well, how do you follow that? I mean, Peter Bray's presentation. Well, I'm not going to. I'm going to do something much more sort of focused and narrow, and really pick up a thread that was initially talked about by Naomi earlier, the idea of forgeries and copies. The forgery of coins is as old as coins themselves, which, of course, as many of you will know, dates back to about the middle of the 7th century BC. As soon as people started producing coins, they started copying coins. And we try to interpret the reasons for these copies in various ways. From our 21st century perspective, it's tempting to regard all non-regular coins circulating in any given period as forgeries. Coins made clandestinely with an intent to deceive. But there is increasingly good evidence to show that copies or imitations of coins were also produced for a variety of reasons. Naomi was talking earlier about that particular class of copies in Roman Britain as being produced at a time when there was a shortage of official coin coming into Roman Britain. And we have a monetized economy that was used to having lots of coins. So when that supply started to dry up, the reaction was to start creating new coins. I can take this off now, can't I? So that's one model. But most of the explanations for copying in general have been firmly economically based. And I wonder whether this is the best way of interpreting these things. Are these purely economic models overly simplistic for all the episodes of copying or imitation that we find in the ancient world? And indeed, there are many. Is the reason for episodes of copying always going to have to be economic? I have my suspicions, as you might have guessed, to the contrary. And I'm going to present a couple of examples for work that I've done over the years that kind of suggest that there might be alternative models possible in interpreting what is basically scientific data. The first of these is a phenomenon which was dubbed one of the most remarkable phenomena within the pattern of monetary circulation in antiquity. This was stated by Michael Crawford in 1977, Michael being one of the foremost scholars of the Roman Republican coin series. In particular, with reference to hoards of Roman Republican silver denarii found in Romania. This has been a well-known phenomenon for many decades, and they've been the focus for a considerable number of papers since at least the 1970s, and is often been quite a controversial topic, especially the dating of when these coins appear in Romania, when they were brought into Romania, and also whether these hoards are composed largely of imported Roman denarii, or whether they are composed to a greater or lesser extent by forgeries, Romanian forgeries of Roman denarii. Crawford argued for a start in the mid to late 60s BC from a historical point of view, putting the influx of coins into Romania as a result of an increased need for slaves by the Roman state. Whilst largely agreeing with the historical reasons, others have suggested that the hoards were the result of a series of phases of importation of Roman denarii, starting in 145 BC and continuing to the end of the Republic. This latter view has been soundly rejected by Chris Lockyer, whose statistical work largely suggests dating the first influx to between 75 and 65 BC, so a little earlier than Crawford, but broadly in agreement with it. Lockyer also noted that the composition of the Romanian hoards is remarkably similar to that of Italian hoards deposited around 74 BC, thus supporting a later date and the view that the hoards were drawn from existing coin circulation pools. The proportion of genuine copies in the hoards, as I've said, has also been hotly debated. Crawford in 1980 presented the numismatic argument for the hoards being composed of largely of imported genuine denarii, whereas two Romanian scholars, Cicescu in 1971 and Preda in 1973, argued for a large proportion of the local copies, large proportion of the coins in the hoards being local copies. And this was largely on the basis of finds of dies and of clearly copied coins produced by casting rather than striking. This is a photograph, a rather bad photograph from an old Romanian publication of a series of dies that was found at the site of Telishka, which were actually made from hubbing genuine coins, by hammering genuine coins into the soft bronze die and using this to produce the copies themselves. And thus the argument went round and round. The dating seems to be reasonably well established with Lockyer and Crawford's version, but the proportion of genuine copies to the genuine coins to copies is something which caused a number of problems and provoked in 1992 Chris Lockyer to persuade me to accompany him on a trip around Romania to collect samples of the coins from several of these Republican coin hoards. And I'm the one with the cool shades, by the way. It was the 30th anniversary of this trip last month, which is what provoked me to consider revisiting these data. The hoard sampled included the Bray hoard, which contains cast copies which had been identified by Poenaro and Bordeaux in 1971, and the Parochia hoard with the struck copies identified by Cicescu also in 1971. The Stan Kutza hoard includes small silver ingots, as well as a large number of copies. Other hoards were selected because they were offered, it was pragmatic to do so. And the Shaker Mika hoard was selected, A, because it was quite large, and also because it was one of the hoards that had been selected by Michael Crawford for his original evaluation of the number of copies to regular coins in Romanian hoards. Back in the, a 10% sample of each hoard was taken, and that these coins were then sampled by drilling for analysis. As there's an example of the damage that was inflicted. In this way, a representative sample of metal is retrieved free of any surface effects or corrosion. Back in the UK, another 24 coins from the British Museum and Ashmolean collections were sampled and included for comparison. And the chemical analysis of 173 coins and 2 of the Stan Kutza silver ingots was conducted by the technique of atomic absorption spectroscopy following acid digestion. Looking at the data suggested that the coins identified as copies contained a little more copper than the most of the genuine Republican issues, on the basis, I should point out, of the 24 coins that were regarded as the control group, as it were. But otherwise, looking at the minor and trace elements, there was very little clear apparent structure in the data set. Statistical analysis of the data by Lockyer, which was published in 2008, was problematic because of this lack of so-called dimensionality in the data set. Detailed multivariate analysis suggested that between 14 and 30% of the coins analysed were likely to be copies, and that would translate into broadly similar numbers for all the Romanian hoards, thereby reducing the volume of Roman imports significantly, and by extension, arguments regarding the seriousness, the importance of the slave trade proposed by Crawford. In 2019, I started work on a 5-year ERC-funded project, the funding of which, of course, has brought Peter in to cover my teaching, and I'm very grateful for his efforts on that. The project entails undertaking a large number of new analyses of Roman Republic and late Hellenistic silver coins, using new analytical techniques with greater sensitivity and accuracy, as well as the addition of lead isotope analysis. It occurred to me, therefore, that this might be a good opportunity to revisit the work done in the 1990s and to reanalyze the samples remaining from the 1992 trip with this new analytical technique. The new data are in surprisingly good agreement with the old measurements, and the copper values partially support the original observation that the copies contain slightly more copper than genuine coins. But it is also increasingly apparent that the genuine Roman Republican denarii were struck on much more variable standards than we had previously thought, and that some genuine coins contain significant levels of copper, as you can see by the plot here. Whoop, I can do that. Okay, so this tail end of outliers from the denarii shows that the variability in the new data for Republican silver shows that there is a greater degree of variability in the composition than had previously been thought. This is an important observation for the interpretation of the Romanian hoards. As we get to understand the chemical compositions of Roman Republican silver coinage better, we can see that all Republican coins are not the same, and that we have to be very careful what we compare the Romanian copies with in terms to understand this phenomenon better. If we go to another stage, another load of plots, another dots on a plot, this shows a comparison between the new data, the grey circles of all Republican coins, all 750 Republican coins that have been analysed to date, and the reanalyses of the Republican coins in the Romanian hoards, which are the yellow dots with the red circles and the other red figures there. This is using multivariate statistical technique, principal components analysis, which makes no prior assumptions about the data. It's simply a data exploration technique using all the variables that have been measured. And you can see that there is structure in the new Republican data, which is a topic for another time, but clearly there are clusters there, clusters born of composition, which need to be understood. And again, underlying the point that these things are very varied. But I think for the point of this talk, it's the fact that the Republican denarii sit well within the main cluster of what we can now say is a general composition. But there are exceptions, and these are these groups down here. And interestingly enough, these exceptions just happen to be the coins in the Romanian hoards that are identified as copies. These are the ingots and the cast copies from Bray and the struck copy from the Poroshkia hoard. They are chemically different, as we can see from this plot. Not a great significant difference, but a significant metallurgical difference. Now, Peter mentioned lead isotope analysis in his paper previously. And lead isotope analysis is an analytical technique that, as many of you will know, which is focused firmly on provenance work. It is often regarded as the preferred technique for the investigation of provenance of material. So I couldn't really ignore this technique and was able to get funding to look at a small subset of the group of Romanian Republican coins. We included these coins here, these cast and numismatically identified copies, and also 5 of the so-called genuine denarii from a selection of the Romanian hoards. The results were not what I was expecting at all. This, unfortunately, is the standard way of presenting lead isotope data. 2 biplots where you get the combination of the pairs of isotopes that the lead isotope measurements present you with. And the Romanian hoard coins, which are the larger markers here, are compared with data sets of lead isotope data for the most likely candidates for supplying of silver at this period, plus the known ancient mining sites in Romania, namely the site of Rosia Montana, which has recently been investigated, and known ancient mining sites that supplied silver to Republican Rome, notably several parts of Spain, the massive Central region of France, and silver mines in Sardinia. It's immediately apparent that the 10 samples split almost equally between the copies down here and the genuine coins here, which is mirrored here. Here's the copies, the genuine coin, the genuine coins here, and here are the copies. And they both map on to particular groups of the lead isotope fields. This, of course, is in agreement with the chemistry that we saw earlier, that there is a difference between the composition of the copies and of the regular coins. The copies themselves group close to the field defining silver sources in the southwest of Spain. And the genuine coins group in between the 2 main clusters of data points and close to the massive Central field. It is also clear that there is no convincing match with either of the groups of Romanian material with Romanian silver sources. This single plot shows lead isotope analyses of Roman Republican denarii published in 2000 as the result of a German project looking at Roman Republican coinage. And it kind of begins to explain what we're seeing in the previous lead isotope plots. The markers are colored according to date, although that is of no great importance at this point. What we have here is a cluster of points down here and a cluster of points up there. The ellipses correspond to the isotope fields of the different regions that were used in the previous plot. Here we have the red ellipse is the Rio Tinto region of Spain. The purple ellipse and the green ellipse are mining regions of southeast and southwest Spain. The blue ellipse is the massive Central region of France, and the pale green ellipse is Sardinia. We can see that the coin points, the triangles, fall into some of these ellipses. Certainly, we can see that the southwest Spain answers the ellipses or fits into the ellipses for the coins in this part of the graph. Rio Tinto, perhaps, these coins here, and Sardinia, some of these other coins, arguably the massive Central region there. But of course, Spain is a single entity, and metal from Spain would have been mixed and combined in coinage production. And this is what the black line signifies here. This is a mixing line between the Rio Tinto region of Spain and the other regions of Spain. And a lot of these coin points fall across that line. This was explained in the publication as showing that the silver used in the Republican period is largely Spanish. You do not have to include the Massive Central region in that equation to answer that question. And I should also point out, perhaps, that these data points fit quite nicely with the Romanian material that we've seen earlier. It's clear from the chemical analysis that Roman Republican denarii were made from silver obtained from a variety of sources that have yet to be properly investigated. But the raw data tell us that all the Republican denarii are not the same. I'll reiterate that point. This reflects the variety of sources, production systems, and standards. The small amount of lead isotope data fit well with the data from the Berlin project, and these in turn fit well with the data from known Roman silver production regions. There is no clear evidence for the use of Romanian silver in any of the coins analysed by lead isotopes, and the agreement with the chemical data suggests that the same is likely to be the case for the other denarii from Romanian hoards analysed. But of course, this does not preclude the recycling of Roman denarii in Romania, as indeed is suggested from the presence of the ingots from the Stankutsa hoard. And the slight reduction of fineness in the ingot and the Breaza cast copies may also point to this. But the metal being recycled is not local and is isotopically consistent with metal of Spanish origin, the same as many of the Roman denarii. What this may mean for the archaeological interpretations of these hoards is complex, but it would seem that simple ideas of importing coins and copying them using local metal will not work, and other avenues will have to be explored alongside further analyses in order to explain this behavior. My second case study, moving back a couple of centuries and moving further east, looking at the Athenian tetradrachm, the so-called dollar of the ancient Levant, perhaps. It was the dominant trade coin in the Eastern Mediterranean, and they've been found in Egypt, Mesopotamia, and throughout the Levant. In Egypt, they were copied by the ruling Persian satraps, often having Aramaic legends replacing the name of Athens, as we can see on this example here. There's the name of Athens, Athe there, which has been then changed for an inscription carrying the name of the satrap at this particular point in time. But the majority of Athenian owls found in the Levant are almost undistinguishable from the genuine coins, and the criteria by which imitations are identified have become controversial, usually involving subjective determinations of poor or bad workmanship. In 2009, I was asked to investigate a group of 20 Levantine coins using ICP analysis. 11 coins, which is mainly this plate here, 11 coins from a single site, the site at Tel Michal, near Jaffa, and 9 coins from various excavations at other sites across Israel. Only 5 of the coins were identified as imitations on the basis of style. I shall now show a very bad map, which is just to give some idea of the spread of the sites. There's Jaffa, so Tel Michal is near there. We have material from Ashkelon, from Lachish, from sites near Haifa up in the north. So covering quite a widespread area of the ancient Levant. Metallurgically speaking, the elements gold and bismuth are those most likely to pass from ore to metal, relatively unchanged through the smelting and refining processes. And therefore they are the trace or minor and trace elements which are traditionally used to try to understand the origins of ancient silver. Here we have a graph of the gold and bismuth contents of the Levantine coins compared to some data, some legacy data produced from the analysis of coins from a hoard of Greek coins found in Egypt in the 1960s, the Asyut hoard. And I think it's fairly apparent that there is complete overlap between the Athenian coins, the Athenian tetradrams from the Asyut hoard, which are, I should add, regarded as being genuine Athenian tetradrams, compared to the Levantine material. I put in some data for coins from Lydia, from the Persian Empire, just to show that there is some overlap there as well. So these pictures are as always, far from clear. But the main point is that the composition on the basis of gold and bismuth context of the examples of Athenian tetradrams found in the Levant seems to be indistinguishable again from the genuine article. If we then again go back to multivariate statistics and we apply the same process, principal components analyses for all the measured values from these coins, and again compare them to the so-called genuine coins from the Asyut hoard, we see a reinforcement of that view. There is an overlap again between these coins. And I should point out on both plots, and I'll bring it up here, that the named points, Samaria, Ashkelon, Tel Michal, etc., these were the coins that were highlighted in the illustration as being the coins identified stylistically, identified in inverted commas, stylistically as being copies. There is no clear connection between these copies and the genuine article. So we reverted to lead isotope analysis just to see whether this could give any additional resolution to the question. Again, we've got the two biplots, and again, we're showing the data of the coins themselves, which are the blue squares in both cases, against a background of published data for silver sources in the Aegean world and beyond, the most likely sources for silver at that period in the Levant. And the results are really quite clear in this particular case. All of the coins, both genuine and stylistically unofficial coins, imitative coins, are produced from Greek silver. Not only Greek silver, but predominantly silver from Attica, from Lavrium. There is a possibility, again, as with the Spanish example, that there is going to be some mixing between Attic silver and silver from northern Greece, specifically from Halkidiki and from the island of Thasos, which we know were producing silver at the time. But predominantly, we're looking at Attic silver. There is no difference in terms of the origin of the putative copies from the genuine coins. What does this tell us about copies of Athenian tetradrams in the Levant? Well, stylistically, recent papers, specifically by Jack Kroll, have made the point that Athenian tetradrams were produced over a large period of time, and that stylistically they vary considerably. He makes the point that poor style is not a good indicator of an imitation, and I think the chemistry backs this up. The chemistry cannot distinguish genuine from imitation, as we've just seen, I hope. The lead isotopes don't really help with the distinguishing copy from genuine article, but they do tell us, in a rather rare occasion where lead isotopes tell us where metal is coming from, that the imitations are made of Greek silver. Not Anatolian silver, not Iranian silver, which would be, for the Levant, perfectly viable options for the silver source at this particular period. So are there any good imitations? Are there any bad imitations? Or are they all genuine Athenian owls of varying quality? We recently, well, not that recently, we went into print making the point that maybe what you're seeing here is the recycling of genuine coins into imitated coins. Why would that be done? What's the underlying motivation from taking one product, of taking silver, imported silver, and converting it into something that looks like the source of that imported silver? But clearly, again, we have an example where copies are either not being made or they're being made from the silver of imported genuine coins. Food for thought, I would suggest. So what have we learned from two little examples of the scientific analysis of forgeries? I think one thing, certainly with the Athenian example, is the tendency for overclassification, certainly by numismatists. Very easy to subdivide and subdivide and subdivide class by class by class, just simply because you can. Whether this signifies anything of historical archaeological merit is another point. And I think we ought to review our terminology in terms of what is a copy, what is an imitation, what is a forgery. I think it's very important to jettison the idea of fraudulent production of coins where there's no evidence for it. And that simplistic interpretations based purely on style can be wrong. And I think this is where archaeological science can contribute to the discussion. It can provide another set of metrics, another set of variables against which hypotheses can be tested. Appropriately applied scientific investigation can inform these discussions, although it will not always agree with the traditional explanations. I think this is important in order to move the argument along. We certainly need to reevaluate some of our ideas about copying of coinage. And with the help of analytical techniques, we can perhaps build a body of data which will enable us to do this in a positive and coherent way. Thank you very much.
Thank you, Matthew. Does anyone have any questions? Thinking about, I think returning to the idea of kind of this question of what we consider to be a forgery and how we sort of interpret that is sort of comes back to the question that Pete asked, I think, about sort of Naomi. Do you think, in what context, we seem to be seeing patterns where repeatedly things are being made out of metals, which from our sort of naive perspective, I suppose, from my own, I suppose, thinking are sort of equivalent materials? Can you say a bit more about the sort of interpretation you're putting on that? What do you think that's significance that is for you? If they're sort of real materials, but sort of fake imitation coins, where that takes us?
I think it varies very much from time to time and place, which is very convenient, I know. I mean, without not coming down with a sort of a canonical view on things, but I think, you know, human beings, we know, are very varied in their responses to given situations and criteria and what is available, and what is available at a price, and I use that term loosely in terms of logistics and resources, to produce the end result. And of course, we don't know what the meaning of imported exotic artifacts, especially maybe, say, in the case of Dacian society, which wasn't a monetized society. These things were coming in. They obviously meant something within that culture other than money. They had a status, they had a kudos, if you like, beyond the purely monetary. Is this what we're seeing here? I don't know. I think before we understand Roman Republican coinage properly in all its emerging variation, we can't really understand the copies of Republican coinage properly. Because I think, yes, I mean, the archaeological record reveals that there were certainly at least two methods of the production of these copies. One was casting, one was striking from hub dies. Very different modes of production. Why was this? Is this just purely one place does it this way, the other place does it that way? Or is there something more fundamental in terms of that, in terms of the way, what these things meant in terms of production? What were they copying? This is something which has not been addressed yet, which is going to be very interesting if anybody gets around to doing that. Yeah, as I think I mentioned earlier, I was at a conference in Warsaw on Friday, where I gave a longer version of this paper. And there was some interesting comments about current work that's been done in Eastern Europe, which is full of copies of all sorts, right the way through from the sort of the 1st century BC right the way through into the early medieval period, in fact. And they're all different. And this is something that seems to be coming out of this, is the plethora of difference and different responses to what must be different situations. I mean, you know, Naomi's work at the beginning talking about a very specific, quite tightly chronologically constrained period of copying in Roman Britain, which was obviously a response to a certain set of criteria at that time. And I think this is the beauty that we can get out of these data. We can start thinking about the way people related to different types of metal and material from different sources. Does that answer your question?
Yeah, I think so. It was certainly an enjoyable answer. Does anyone else have any questions?
I mean, obviously, I don't know period one little bit, so coming up from the outside, do we know anything from the, is there anything in the text which tells us that people are concerned about copies?
Yes.
Or, okay, right.
But specific sorts of copies.
Okay.
Certainly, there is a very well-known reference in Pliny, which is basically a way of just defaming Mark Antony, saying what Mark Antony did, and this is the end of the Roman Republican period. What he did was adulterate the coins with iron, and that this was something that he was to be complained about and put down because of it. As it is, Pliny, as is so often the case, is actually wrong, because you can't mix silver with iron, it doesn't work. Iron has much too high a melting point, etc. There's technological reasons for this. But yes, they were very concerned about this. We know they're very concerned from an archaeological perspective, because at various points during the Republican period, the mint actually nicked the edges of the coins to expose the metal within, because the method of forgery, and I stress that, fraudulent forgery, was to produce a copper blank, cover it with a thin layer of silver foil, and then strike that and pass that off as the genuine article. That's what they were concerned with at that point, was fraudulent forgery. Now, how these imitative coins fit into that picture is something that people are discussing and argue about. Because there are various levels of copying. And I think this is something that we find in all contexts, that copies were done by different people for different reasons, even at the same time. And that there is a great variety of these things. It's not at all simple. And I think that's been the problem. People have been trying to apply very simple interpretations to data which are really rather complex.
To the point of emerging complexity and all the sort of approaches to archaeological science. Well, are there any more questions, Matthew? If not, then let's thank you again. We're moving on to our final paper of this session. Dr. Juliet Spedding, who's going to move us away from metals, at least briefly. I'm not going to end that again. I nearly made the same mistake as earlier on. And move us on to look similar kinds of questions, but in a different material, looking at the processes of reuse and recycling. Yeah, I think it's just here. This process of reuse and recycling in glass materials, which is a topic which again has been emerging in the last, I guess, over the last sort of decade, and particularly over the last sort of 5 or 6 years, as a really important kind of focus of archaeomaterials research. Dr. Juliet Spedding I was a PhD student at the University of Liverpool, and she's going to talk about reduce, reduce, reuse, recycle, the identifying, reheating, recycling, and local imitation, and the history of glass in Nubia. Juliet.
Yeah, I apologise for the title. It's a work in progress. Okay, thank you to Pete for suggesting or offering me a place at the conference last week. I rashly decided to say yes to. So this one is something that came out of my PhD thesis and sort of idea I'm sort of going to float today. So I'm going to just start off to bring you up to speed as to what ancient glass is made of, as I appreciate predominantly this room is full of people who do metals, or if they don't look at that, they certainly don't look at vitreous. So we could describe it as a silica lime soda mix, or a soda lime silica mix. I've probably got the words in the wrong order. So what does this involve? You've got the silica, which is known as the network former, from sand, desert, river, beach, or quartz pebbles. The problem with silica is it has a melting temperature of 1,720 degrees C, which is not something you're going to achieve with your ancient pyrotechnologies. But people in the past are nothing if not inventive. This is where the soda, or the network modifier, comes along, nature on a plant ash. And as the name suggests again, it modifies the network, brings that temperature down to 1,000 degrees C, which is all well and good, except for the fact that this combination is incredibly unstable and will decay very easily. Now, glass will certainly decay, but it generally takes a few thousand years and a lot of water to do it. This, however, would decay a lot more quickly. But then you get the lime, which is the network stabilizer. And this is either you have contaminants in the sand, so shells, for example, or they're adding it intentionally. And as the name suggests, this stabilizes the whole network, and there you get the glass that can last for thousands of years. You also get your colorants. So you've got copper, you've got cobalt, manganese can be a colorant and a decolorant, iron either accidentally added through sand or intentionally added, and you've got antimony also as a decolorant. So I'm going to take you briefly through a sort of whistle stop of my PhD research before then focusing more on the recycling aspect. So here is Nubia, and the 4 sites that I looked at material were from Baras, Casa Ibram, and Gabati and Merowe, right down here in the south. Time period wise, for Nubia, it's what's known as the Meroitic period, so 400 BCE to 400 CE, which corresponds in Egypt to late period, Ptolemaic period, and Roman period. We then get into the X group, or now it's more commonly known as the Bolana culture, for 400 to 600 CE. So what did my research involve? Well, it involved ultimately the finished product was 192 samples of non-decayed glass from 4 Nubian sites. I say non-decayed because I actually had 373 samples. So a good proportion of those had decayed. It wasn't just beads, I was also able to look at vessel fragments because the possibility of comparing the differences and approaches and things as a result of your final finished product. Chemical analysis was performed by scanning electron microscope with energy dispersive spectrometry, but I also had the opportunity to do lead isotopes on 13 samples with the LAMC ICP MS down in Nottingham. And whilst crudely put, this was basically the impetus for looking at the stuff. What is in it? No one has really looked at this stuff. What's in it? And that leads to the larger question of how does it relate to the glass making, the glass working, and trade from across the Mediterranean world. So the overall findings of this showed that glass from the sites of Pharos in Merowe, Pergamon in Turkey, Bubastis in Egypt, and Butrint in Albania showed a very similar composition. So similar, you could argue they were using the same raw materials, so chances are they could have been coming from the same very large primary production center. Glass groups identified for Pharos and beads were the three Roman decolored groups using manganese, antimony, and combination, and what's called in a more recent group discovered at Bubastis, the weak HIMT, so weak, high in iron, manganese, and titanium. For Barty, we've just got the Roman ones, but there is caution needed with this, and you'll see later. Merowe was where I have my vessel fragments from, and they show very clearly to belong to these Roman decolored glass groups. An interesting result of this was the discovery of Indian-made glass found at the site of Pharos. Here's an example of one of them. So these ones came from the British Museum. You can see they're a wonderful orange opaque glass. I chose them because orange glass was quite an unusual thing to see in the catalogue, and I wanted to find out what was in them. And it turns out these are actually the high aluminum mineral soda glasses from India. I also came across the technologically very advanced high lead red glass, which was found at the sites of Pharos, Kabati, and Merowe. When looking at them through a principal component analysis, it showed chemically they are very different. So indication of different production centers, different raw materials. Could they have been made locally? Here, I should stress, I'm not necessarily saying they were made locally in Nubia, although I would like that to be the case, but made at a more local level than the primary production centers, which produce glass by the tonnage. They were producing tons in one go. And here's an example of what I mean by these high lead red glasses. You've got a very pillar box sort of really good red color with a green patina on the surface. Interestingly enough, when Griffith came across some of these an excavation at Pharos, he initially thought they were green glass because they were completely covered in green patina. Only after I'd sampled them was it revealed that they were actually this red glass. And what I also found from having an awful lot of decayed samples was that the presence of high levels of lead in the glass can help it resist decay. So I had glass from the same graves that had high lead and low lead. The low lead glasses have completely decayed, but the high lead ones have stayed undecayed. So there is this question of the extent lead can actually protect against decay. And finally, thanks to being able to use isotopes, lead isotopes, I was able to potentially identify Turkish and/or Greek sources for the lead in these high lead glasses from Nubia, which again leads to all sorts of questions as to the source of the lead and how it's eventually getting down there. But that's for another day. So, and there were always more questions and answers as a result of this. So there were glass samples from Pharos and Kabati that didn't fit, as it were, into the known glass groups of the Mediterranean. We also have the presence of the Roman manganese and antimony glass group at Merowe, which we suspect is a glass group from the result of mixing. Which leads to another question, could you be recycling on site? Is there the ability to recycle on site? Could you be reheating beads at Pharos? And I have these interesting ones at Kabati, which are a liver brown red color, high in manganese. Could they be a form of imitation of the high lead ones you also see at Kabati? Calci Ibram. They certainly look like a glass. They have been identified as a glass, but they aren't one. They are not glass. But could we be looking at something that has potential to be locally made? So I'll just go through them site by site and just looking at them. So first we start off with Pharos, circled up there. It was in ancient Nubia. It's now in modern day Egypt. It's also under Lake Nasser. So it's gone, the site's lost. This is an example of what was lost. This is the cemetery at Pharos that Griffith excavated, which my material came from. I think the numbers of graves go up to like 3,000. So an awful lot. I mean, this is just one area of one site that was a major site during this time period. The Pharos samples were all beads. They are Meroitic period and X-group culture date. We come across 14 graves. It was from Manchester and the British Museum. I had 187 glass samples. Unfortunately, it's only 72 hadn't decayed. So when looking at the non-leaded ones, as I'm only going to be focusing on them, the high lead are a completely separate entity. Using principal component analysis, I could identify the weak HIMT, present, Roman, antimony, manganese, and antimony. But there, as you can see, we've got some outliers going on here. So in the interest of trying to see, potentially identify a glass group, I looked at some glass groups that are slightly later date in the possibility that they could relate. And there's not really what I call, I can't be confident in a correlation there. I mean, you've got the HOMT up here, Foy 2 and Levantine 1, but there's nothing really that corresponds. So instead I started looking at certain components, which when I looked at the data itself, and I actually looked at the numbers, showed sort of, they were quite high in comparison to the other ones. So it related to the outliers from the previous graph that they showed these higher levels. And these are actually levels of particular compounds that can be associated with reheating, recycling, and reuse, particularly the magnesia, the lime, manganese oxide, phosphorus, potash, and iron. And certainly the potassium and the manganese could be introduced with the reheating due to results of the fire being used, which Painter has looked at with her experimental work. Phosphorus, again, is something else that could be introduced during that process. Iron from the tools, potentially, could be reintroduced that way. So this is where I came to be thinking, because these objects, as I said before, were beads, they're not vessel fragments. I'm wondering about the terminology. So when we have something that gets remade, we would refer to recycling as a sort of a blanket term. But then came the question of reheating versus recycling. So when it comes to reheating, really you don't need to heat it enough to make it soft to work. Now with glass beads, you could see that be quite straightforward. You heat it to be soft enough to work, you wrap it around a mandrel, is ideal for beads. You could do it on a slightly smaller scale potentially, and you could certainly do it from bits of broken glass. You get glass rods being made and then heated up and then used. So why not be able to also do it on smaller bits of broken glass? So potentially then you might not require the same level of skill that you would if you were completely making a vessel, but there will undoubtedly be a level of skill required. When it comes to recycling, you would need to completely remelt the broken glass. And this is really necessary for vessel fragments. In the ancient world, when you get to the point where glass blowing is making glass more sort of available, as it were, it's these colorless glass vessels that were the height of production. They were the ones that showed you were the true sort of the wealthy. If you had colorless glass vessels on your dining room table, that showed you were very wealthy. You're not going to want something that looks like it's been pieced together from broken bits of glass. So you could argue it might need a higher level of skill to produce the finished vessel, so through glass blowing and molding. And this is still a work in progress, but I think it's important to distinguish the difference between a reheating process versus a recycling process. So Gabati. So we're down in the south now, 40 kilometers north of the Royal Capital at Merowe. And this was a Meroitic, post-Meroitic and medieval cemetery discovered in 1993 by the SARS survey team due to the fact that a road was going to be built through the area. I believe now a road has been built through it. So again, another site that's gone. Again, we're looking at beads, but we're only looking at Meroitic period date. 3 graves, and they're from the British Museum. Only 23 of these haven't decayed. But what is wonderful about a more modern excavation is that they did some C14 dating from material in grade 55 to get a 60 to 240 CE rough date. And thanks to the same pottery assemblages across the 3 grades, you could give a sort of a rough date for those as well. Now, when these went into principal component analysis, just like the ferrous ones, again, well, nothing to do with the weak HOMT, there's no relation there. Some with the antimony, and some with the manganese and the Roman manganese and antimony. But again, we've got some outliers. So again, compared them to the later ones, but there is absolutely no overlap here to explain what was going on. Unfortunately, unlike the ferrous ones, there was nothing in those previous components to indicate that there was any reheating could be argued, or certainly the compounds that you would indicate reheating and recycling going on. But what was interesting about them was, aside from the fact that they were liver brown red color, was that this high manganese level, well over 1%. And visually, when I got hold of them from the British Museum, they did visually look a fair bit like the high lead ones. We also, from this one, the Gabati high lead beads were compositionally very different to the ferrous and Merowe beads. And we also have high lead found at the Royal Capital Merowe, which is only 40 kilometers upstream. It's not a great distance. So could we instead be looking at something that's like local imitation? Are they attempting to imitate a very technologically demanding, and maybe then arguably a very exclusive form of glass that showed a certain wealth and status, and they're doing it through the use of this high manganese? We then have to take into account control of the furnace environment and things like that. But could we be instead looking at something that's more a local imitation? Because like I said, visually, they're quite hard to tell apart. Merowe, the royal capital, right down there midway between the 5th and 6th cataracts. These were excavated by Garstang. So the best I can say for the provenance is it's a bit tricky to know the exact provenance of small pieces that were picked up off the ground. This material came from the Liverpool Well Museum, Peach Museum, and the Garstang Museum, and unlike the others, these are vessel fragments. Colourless vessel fragments to be exact, or with a slight tinge of green to potentially already indicate that they've been mixed with something else. We'd identify them as the Roman manganese antimony, manganese and antimony glass group. And we suspect that the Roman manganese and antimony glass group is a result of mixing of glasses. Vessel fragments, as I suggested before, would need to be fully recycled to get a usable product out at the end of it. But from other work done at Merowe, we know due to the presence of iron slag and there are iron ores that there was at least iron working facilities at this site. So we already have this control of pyrotechnology present. It's also been suggested that they've found glass working slag at the site as well. And it's important to distinguish glass making from glass working when you're looking at glass in any context. So what this means is pyrotechnology is present at the site, and knowledge and way to work pyrotechnology is present at the site. Therefore, there is the potential to have the facilities to recycle the glass at the site. That's sort of as far as I'm going with it at this point, to say that you've got these pyrotechnologies here, you have the evidence, extensive evidence of iron working going on. So you have the potential then to recycle glass at the site. But why would you? Merowe is the royal capital. It will have connections with Egypt and the Mediterranean world that other sites could only dream of. So why would you recycle? Well, a possibility is when you get an interruption to trade routes in your supply. So the Roman-Meroitic War could provide, for example, an example of such an interruption. So in 25 BCE, there was a revolt in the Tricon Tassionis. A lot of things, and this covered the area of Upper Egypt and Nubia, a lot of things were causing problems, but predominantly they were fed up of paying taxes to Rome. And it wasn't until at least 5 years later that, following an awful lot of skirmishes and the Romans discovering that they couldn't hold Nubia beyond the Second Cataract, that Lower Nubia was divided between Rome and Merowe, the frontier being drawn at Tonkuso and Hierosypmonis. So you have this 5-year place where they've got all these skirmishes, you've got a garrison stationed at Casa Ibram, so you have potential interruptions. Another one that could also cause disruption to your trade routes is certainly when you have the inevitable decline and collapse of the Meroitic Kingdom. Can these cause an interruption to glass supply? Or rather, could such events be the stimulus for something that may have already been practiced on a very small scale? Interrupted when people were sort of still demanding glass and breaking it, that they decided that they were going to perhaps up the amount of recycling potential at the site. We have these facilities, we have the pyrotechnology, so there's the potential then that we might actually have the stimulus to make a wider use of recycling. And finally, Casa Ibram. This one was also in Lower Nubia in the ancient past, currently in Egypt, and has suffered as well from the waters of Lake Nasser. 13 samples from the British Museum, X-group Balana culture date. They were all beads and they look like a green glass. If you looked at them, you couldn't tell the difference.
hence why we need to do scientific analysis on an awful lot of things. But they are not glass. The silica levels alone sort of showed that they weren't, with over 80% levels. But I was very glad I used SEM analysis on this and hadn't dissolved them in nasty formic acid, because I could get a visual to try to understand what was going on. Now, this is a sample of glass from ferrous. This is, generally speaking, what you want to see when you stick ancient glass under the SEM. And I will be the first to say it looks incredibly boring, but this is what you want. I mean, corroded glass looks wonderful. It looks like tree rings, but when you see it, it's like I've just spent weeks preparing a sample and now it's decayed. This is what you want. These are the Casa Ibram beads. So we've got all of these sort of silica grains. We've got a few sort of voids here. We don't really have any evidence of an interaction layer or a glaze layer, as you might find in faience. However, if I compare it to faience, and there is undeniably a similarity. So on the bottom here is a piece of Meroitic period faience from Nubia, from Meroe itself. Meroitic faience is not particularly great. It's not particularly well made faience. Some of the samples I got given fell apart as they were sort of lifted up off the string. They sampled themselves, which was very handy from that point of view. So you see we've got this interaction layer here, we've got the evidence for the glazing, and we've got the body. So in an effort to try to identify what this stuff might be, I had a look around. Now, initially, well, I had stuff from India at Ferrous. Casa Ibram is further north than Ferrous. And there are some green glass beads from Sri Lanka that bore a striking resemblance, but when certain numbers were compared, wasn't really any similarity. So instead, I went looking for other materials. Frit from Amana being the first one I came across. And we can see in the silica levels, they are quite similar. Soda levels are as well. Lime is off, and due to the fact that you're using a different sand source, the aluminium will be different because the aluminium contaminants in the sand will be different as well. But there's also another possibility, and whilst I'm not a fan of using these terms, they are still used in literature, so I will have to. Variant E or glassy faience. And again, the silica levels, they're not as tight as the Frit, but they are quite close. Soda's a little different as well. So are these essentially a glassy faience? Could they have originally been intended to be a faience that they might have, say, left in the oven too long, for example? And like I said, visually, they look like a glass. So could they again be a form of local imitation? Are they trying to imitate a glass? Because even when you have taken a pair of pliers to them and can see the inside of them, you cannot see a structure as you would see in faience. You can usually tell with the faience, you could just see either the sort of the white, the off-white. You can tell visually it will look like a faience, but this stuff was very smooth. You have angular grains, which indicates they've been crushed by hand and not weathered. So another thought that occurred to me, could we actually be seeing the reuse of broken vitreous materials? So metals are intrinsically recyclable. Glass is now coming to be recognized. You can recycle ceramics, but why not recycle faience to make other faience? You have the ingredients there, you have the raw materials there. All you have to do is, if you've broken a bowl or you've got numerous broken beads, is to crush them up together, heat them, and then you get your object. So this may lead then, you have questions about the potential for a more local cottage industry that could be happening in Casa Ibram. And it should be remembered that these beads date to after the collapse of the Meroitic period. So following the Meroitic period collapse, we get the Balana culture up only in the north of Nubia. So certain trade routes could have broken down. So again, we have this interruption to potential supplies. So maybe out of necessity, people are just recycling things more often than they would. I mean, people of the past were considerably less wasteful than we are today. So again, do we have this impetus to make stuff out of what we've got lying around? Or is this generally what's been happening anyway, and we've just sort of never really kind of considered it? And the raw materials of faience are lying around the desert in a very literal way. So we'd never think, oh, well, you know, perhaps they just went and got some more, but what if they are actually, when this stuff gets broken, simply crushing it back together and reheating it to make more? So what could I conclude from all of this? Well, we may have potential evidence for site level manipulation, imitation of imported glass. I stress may at this point, that's still a work in progress. But the importance of being able to detect mixing and reworking would give us more of an insight into the biography of an object. So it's not just simply raw materials made, object ends up in the ground. We could need to think about all these other stages that are going on to how people were interacting with materials, how they saw materials. So we have to, there is undeniably certainly a creativeness and inventiveness of craft practices in Nubia, how they approached their objects and what they did when certain economic and political situations might have got in the way. And I think this is something that always needs to be stressed. I mean, provenance and sort of studies may be a key example of this. We always want to look at the big stuff, the international. How far did this material travel? How far did it go? And sometimes that may result in a tendency to forget what's going on at site level, the smaller home-based practices. And really, we need to look at both. We need to know, we need to establish how far the materials were traveling to know about interactions, but we also can't forget there's more smaller home-based practices that were going on in response to the trade of the new stuff coming in reaction, or because that stuff actually stopped coming in or was significantly reduced. And so we have that aspect of, that's the pretty stuff, I can't possibly make that, but I can imitate it and sell it for something that's quite close. So you have that sort of aspect of people finding a way to kind of cheat the system, as it were, perhaps. But I think that's an important thing to consider, both the international trade level and the small home-based practices. Thank you.
Thanks, Juliet. It's nice to see people thinking about these ways of sort of different forms of recycling. I know that's something which has been at the forefront of people's minds over the last few years. So it's hearing in glass as well. That's great. Does anyone have any questions?
I love the idea of recycling failures. I think that's fantastic. What's the current thinking about what's been identified as frit in Oman? If you got better way in by saying that could be recycled vitreous material as well.
I mean, it might be. The material that I was using in that was based on Shortland's study from the 2000s. I'm not entirely sure, because like I said, this material is actually just lies around the desert. Although having said that, desert sand isn't the best stuff to use. So I do wonder if people just thought, oh, they'll just go and create new, or they'll just create it from new, they'll just create it from new raw materials, which might be an example of us projecting backwards, because very much in the modern mind, something breaks, I'm not going to super glue it back together, I'll just get a new one off Amazon. So I suppose there is this potential then that if you've already got the material made, you've already got the components set together, crushing it up is going to be a much easier process than schlepping out into the desert to bring it back or waiting for the stuff to come in. And people in the past are not going to want to do anything that makes their lives any more difficult than it is already. So I don't know, from the point of view of frit, I've not really looked at frit at all in the aspect of vitreous materials, but it could be a possibility that broken pieces could have been used for the frit, and then that would then be used to make the glass. So we've already got recycling at that very basic level.
Sorry, are you also seeing relatively high levels of the manganese antimony groups outside of the Mediterranean, or are they relatively common throughout, if you see what I mean?
Well, I was sort of, certainly they haven't really been identified in Nubia. And I mean, admittedly, some of mine are coloured. So again, this is why I'm thinking about reheating and like the use, except for the Meritic period ones. You do get the Roman manganese stuff in Britain. So you get all those three glass groups in Britain, which gave me the idea of interrupted glass supply, because it seems then that certain ones kind of vanished when the Romans vanished as well. But because we know that, we suspect that one is the result of mixing, and then gives the question of, could they just be then just throwing it in unknowingly, or do they actually know? And is there a distinction between the manganese coloured and the antimony coloured? Because antimony is present in glass for the high lead runs. The recipe first appears in Assyria in the 8th to 7th centuries BCE, and the Akkadian redstone recipe and the other one, redstone recipe, there's translated as a shekel of antimony, and half a shekel of antimony is being used in the actual recipe that they have written down. And experimental work, I think, done by Brill kind of confirmed this. An analysis of material from Nimrud and Persepolis actually showed very high levels of antimony, and my ones also had antimony in them as well. In fact, if they hadn't been coloured, I would have considered them a Roman antimeter coloured glass through the levels of antimony present. But it was a great way to date the Meroitic period stuff, because as I said, they're excavated by Garstang. We know the glass groups, they're about 1st to 3rd centuries CE. It was an excellent way for me to narrow down 800 years of possible dating history to 400. But yeah, so you get it in Britain, so they went with the Romans.
With all the kind of caveats associated with Garstang's excavations, have you got enough contextual information to give you any idea about any separation or associations of these particular, whether there's anything interesting about the context in which they were found, or is this?
Nope.
No,
nothing. I have it was Meroe, I have it was Meroitic period, I have it was Nubia. That's actually quite good, given that they're actually just little pieces, they're just little vessel fragments.
And they weren't sort of associated together in any way beyond.
Not that I know of, no, it was just simply, there were museums in London up here, and it was just, it's Garstang, you kind of just accept the fact that you're not going to get very detailed provenance in these things. Hence why I was glad I could use the glass groups to at least give a time period from when they were made.
Sure. Well, that was a very easy answer to my question.
Sorry, yes, I'm afraid if it's Garstang, you're not, unless it's a really big object or a really impressive object, a coffin statue. If it's something like this, it got noticed enough to be picked off the ground and noticed that it was from Meroe, but that's the best you're going to get.
Well, I suppose that's something.
And I went through his notebooks as that we have them, and just, well, there is glass in this location here and this location here, but and the iron working facilities weren't really sort of first discussed until about, I think, the 1950s. And as you can imagine, the controversy that caused by suggesting that a kingdom in Africa was producing its own iron. We've since learned better. Very recent, more recent work has been done by Jane Humphreys in that area, looking at the iron sites there, because it's just covered in iron slag, and as we know, you're not going to move slag around the place, so it's being done there. There's also the potential for black glass at Meroe, maybe, but you need high levels of iron to produce that. Whether or not they were making it is another matter, because unfortunately glass making facilities in the archaeological record are incredibly scarce, not very easy to find. Glass working, on the other hand, no, you have the, like I said, you've got the pyrotechnologies there, so you can make the suggestion it was happening. But well, you have to see. More evidence would be needed to be found if it can be found.
Hope for more evidence in the future. Well, if there aren't any more questions, then I suggest we take a short break. Well, I think we have sort of 15 minutes just to have refresh ourselves a little, and then we'll return for the final 2 papers of the day. Thanks a lot.
Yeah, so, really?
Yeah.
All right.
Can we just pause the stream? I think if we go up to the top, no, more section there.
Full share.
No.
That's a full share.
That's okay. Oh, yeah, that's okay. Yeah. Thank you. I'll just turn off the mic as well. So I'll sort it out. Sorry. Thanks.
Is it all right?
Yeah. So I thought it was really interesting. Once again, returning first to a sort of combination of metals and but also of lithics with Dr. Tom Elliott, who is a PDRA on the Rackham's project with Matthew, and he's doing some really exciting things with lasers, which is always a good thing to be able to introduce. I mean, what's better than lasers? So let's bring you up and let's talk about the fantastic LAICPMS, or recent approach to flint and metal using LAICPMS. And if I can get it running before you get here, there we go. You're off. Take it away, Tom. Thanks for
that, and thanks for inviting me. As Pete said, I'm Tom Elliott. With a title there, I guess I was invited to this to basically introduce myself to other members of the staff here, as well as kind of give a bit of a background in terms of where I've come from. And I guess I was employed on the Raycon project because of my knowledge of laser ablation. So that's what I'm going to be concentrating on mostly today. Oh, there we go. So yeah. Okay, so in terms of the structure of the talk, I'm going to talk about my PhD as a kind of background, and then move on to talking about my paper that I've just published, where I've basically gone through my PhD data in a lot more detail and offering some sort of opportunities for the future. And then I'll briefly touch on the work I'm doing at the moment as part of the Reheating project. So for those of you who don't know, or maybe just as a bit of revision, what is laser ablation, or LA-ICP-NS? So it stands for laser ablation inductively coupled plasma mass spectrometry, and it's basically a laser instrument linked to a mass spectrometer, and it's used for micro sampling. So in terms of how this works in practice, you have your laser instrument and it fires a ultraviolet laser at your artifact or object. That breaks off a tiny amount of material, which then gets sucked through into the mass spectrometer, and it's broken apart and ionized. And those ions are then separated by the rest of the mass spectrometer and then detected. And so you can work out the proportions of different elements in that material. As we've kind of touched on previously, it was developed in the 1980s in the geosciences, but it's being increasingly used in archaeology on different materials for the past 20 years or so. Hopefully this works. This is just to give you an idea of how it works in practice. What you're seeing here is you're looking down the microscope of the laser instrument at a crater being ablated, and the diameter of the crater is only 50 microns. So you might hear it being described as micro or minimally invasive, or even non-destructive, because it's taking such a small amount of material. And what you'll see is the light flickering in the center, and that's the plasma of the material being ablated by the laser. And then you should see some material coming off as well. So yeah, that was a piece of flint, I should have said. So in terms of the facilities we have here at Liverpool, we have a laser instrument at the MIF next door, the Materials Innovation Factory. And as you can see on this trolley, we've got the laser instrument, and then you can see the sort of clear plastic tubing coming out. That takes the sample into the mass spectrometer, and then the two are controlled by computers. Okay, so for my PhD, this was called the Mesolithic in the Marches, and I did this at the University of Worcester. And the aim of this project was to identify the geological source of Mesolithic flint artifacts from the region in order to evaluate previous hypotheses of mobility. So to do this, I analysed a load of artifacts and then a load of geological samples with laser ablation, and then compared the two with machine learning, which I'll detail in a minute. So in terms of the study area, you can see it's outlined in red here. You've got Hereford in the sort of top centre, and then leading down in green, you've got the Wye Valley area of outstanding natural beauty. And in terms of the study area, environment-wise, you've got a range of different locations, including the sort of very tops of the Black Mountains in the west, the Malvern Hills in the east, and then Herefordshire Plain in the centre, so rolling farmland. And then that leads down into the Wye Gorge and towards the Severn Estuary. So in terms of the previous sort of ideas of where flint's coming from, although there is natural glacial flint in deposits in the study area, this doesn't seem to be what people are using in prehistory. So the question begs, well, where is it coming from? And since the 1870s, you've had a range of different ideas, including the Pembrokeshire coast, glacial deposits at Abergavenny and Gloucestershire around Moreton in Marsh, as well as river terrace deposits for the Bristol and Warwickshire Avon rivers the Severn Valley and the Severn Estuary. And then lastly, the kind of obvious location is the chalk bedrock itself, outlined in green. So in terms of my archaeological sampling, I looked at 12 archaeological sites in the study area, so 118 artifacts in total. Most of these were microliths, or at least artifacts from secure Mesolithic contexts. But I also included a number of surface finds due to the limited number of excavated material in the study area. And then, as well as that, I also included a number of Neolithic artifacts as a bit of a comparison. So in terms of my geological sampling, as I said, I was kind of really trying to target where people had previously looked, or suggested, sorry. So I looked at river terraces, glacial deposits, and kind of beach deposits, and sampled from 14 sites. This is going to be a little annoying. And 145 nodules of flint or pieces of flint from these locations. I then cast my net a bit wider and looked at the chalk bedrock itself, sampling from 21 bedrock sites and 269 nodules of flint from them. These were mostly geological triple SIs, so special sites of scientific interest. And what was important about them is that they're mostly disused quarries with the chalk bedrock being still exposed. And what's important is that there's been extensive geological recording at these sites. So I could basically relate my geological samples back to that geological research to have a really good idea of where they're coming from. What I also wanted to do was a number of sites I collected samples stratigraphically, because previous authors have discussed how there might be a change in the geochemistry of flint stratigraphically, as well as geographically. So this kind of provided the ideal opportunity to really explore that. So here you have me sampling at Peacehaven near Brighton, and Beerhead in Devon. Once I'd collected my samples, I did the analysis at the University of Oxford Department of Earth Sciences, and I analysed everything in triplicate, totaling nearly 1,600 measurements in total. In terms of the elements that I was interested in, again, I was trying to cast my net wide, so I looked at 53 elements to get a really good idea of what's going on in the geochemistry of flint geologically, so then I could understand my artifacts a bit better. So once I'd done my analysis, I'd got my data set. It was then down to kind of comparing the artifacts with my geological samples. Now, to do that, I used machine learning. Now, I'm sure most of you are now aware nowadays that machine learning techniques are basically used to solve mathematical or statistical problems by learning from training data. And these techniques are being increasingly used in archaeology towards things like artifact classification, so categorizing arrowheads or pottery types, as well as identifying undetected sites from remote sensing imagery, and now increasingly towards things like lithic sourcing. The key issues with these techniques is how they're evaluated, the number of samples used to train the models, and most importantly, the choice of which technique is used in the first place. So just to give you a very, very brief introduction, I use a technique called random forests. This is basically models which are generated out of thousands of individual decision trees, which work to best split, say, in my case, your geological sample sites from each other. And then it works on the principle of the wisdom of the crowds of how best to do that. What's random about it is that each stage of the decision tree of how best to split the data, you're using a kind of random variable. So iron or aluminium, are the values greater than or less than this value in order to split the data. You then take a sample of your geological data from those sample sites and test the models on that for a process called cross-validation. This can then give you accuracy scores because you know where those test geological samples have come from. And then you use the best model, i.e. the one with the highest accuracy, to then classify your unknown data, which in my case was the artifacts. So for my analysis, we achieved accuracy of 68% using the F1 score, and that's pretty good. And again, that's in correctly identifying where your test geological samples are coming from. Because we analysed everything in triplicate, that allowed us to go back and really understand what those results were telling us. We found that at least 95% of the time, at least 2 of those 3 measurements for the artifacts agreed on a source. And you can actually even go back even further and understand that on what the problems are. So for example, a lot of the flint from Morton in Marsh is glacial deposits, and those glacial deposits are found elsewhere, and they've made their way into the Warwickshire Avon River Terrace deposits, and then ultimately the Severn Valley and Severn Estuary. So then it's no wonder then that Random Forest is then struggling to differentiate those locations, because it's basically picking up the fact that the flint is very similar. So once I'd kind of done that sort of analysis, I then averaged those triplicate measurements to provide a single answer for each artifact. So in terms of the archaeological implications, for those 12 sites, we found that there was a range of short, medium and long distance, so 200 kilometer plus movements of raw materials or the artifacts themselves throughout the Mesolithic and into the Neolithic, with this material primarily coming from river terrace deposits. Although interestingly, there was quite a clear signal to Peacehaven, so that first site that you saw me abseiling at. And what's the take-home message here is it's not Peacehaven, that site itself, it's the geology that those samples represent. In terms of the kind of assessment of the previous hypotheses of mobility for the region, this is well beyond sort of previous ideas, which mostly concentrated on your kind of classic Mesolithic mobility models of kind of moving from the coast, so the Severn Estuary, Bristol Channel, up into the uplands and back, and having embedded procurement of materials from that. But although this is kind of well beyond those kind of previous ideas, actually when you look at the kind of broader scale of what's going on in Europe, these kind of long distance movements of materials actually is pretty much the norm across Europe throughout the Mesolithic. In terms of sort of interpreting these results, actually, if we look to kind of global trends in the ethnographic research that Peter Toppin has conducted recently for his work on the Neolithic, we might understand that these kind of long distance movements of material likely represent exchange practices, or at least a more complex picture of movement of materials than we'd previously considered. Okay, so that was the PhD. Me and my colleagues who worked on the project, we've since moved on and tried to develop things further. And so we've just published a paper because the first thing we wanted to check was, are we actually even using the best technique machine learning wise? So to do that, we also looked at k-nearest neighbours and support vector machines, which work in different ways, which I won't discuss. So before we did that, what we wanted to do is a series of different analyses to really understand the data that we'd got from laser ablation. So to do that, we first visualize the data using T-distributed stochastic neighbor embedding, or TSNE, which is very similar to a PCA, but it works in a different way. And what this shows is that for the bedrock data on the left, you've got pretty good structure. So if we take Flamborough Head down in the bottom left in red, you can see that's clearly being separated out from the rest of the data. However, for the superficial deposit samples, that's showing porous structure. Now, that is primarily because I didn't collect enough geological samples from your superficial deposit sample sites. And so we ended up grouping them because they were performing poorly. So you can see the Severn Valley, Severn Estuary, Bristol Avon, Warwickshire Avon, and Moreton in Marsh. And each of those regions, as we called them, are composed of multiple sites. And so that's why you're seeing porous structure, as well as the fact that the flint from those deposits is actually mixed. You've got a range of different types of flint. So on that basis, we only used the bedrock data to evaluate the machine learning models, because we wanted a kind of robust foundation in order to evaluate them. As I said, we looked at 53 elements for the PhD, and what we wanted to know was actually which of those are the most useful, the most predictive in working out where your material is coming from. So to do that, we used a technique called recursive feature elimination, whereby you build multiple machine learning models and take away the worst performing element each time. And that allows you to rank basically the predictability or the predictive power or importance of each element. What we found is that the elements that are kind of ranking highest actually are very similar to what's been shown in previous research on other locations, say in France and in Britain itself as well. Now these will have a geochemical basis, so we can use this to inform future research and basically discard those other elements because they're either not helpful or they're actively making things worse by adding noise to the models. One of the problems with using what we call a supervised classification machine learning model is that you're artificially coming up with classes into which you're trying to put your unknown data. The problem with this is that there's no other category. And so to get around this, we implemented this novelty detection, which allows you to at least label your data as either an inlier or an outlier based on the kind of similarity of that data point to others. And importantly, this hasn't actually been done in previous sourcing studies before. So that's a key step that needed to be added, really. What we also wanted to know was, is it even worth going out and collecting more samples? Will that help boost the performance of the machine learning models? So to do that, we generated a learning curve whereby you build more models of random forest again, and each time you're adding more data, and then you can look at the performance, which is the F1 score on the y-axis here. And basically what it shows is, yes, if you're adding more data, the machine learning models find it easier to categorize your sample sites. But there's diminishing returns, and that's probably because by increasing the number of samples, you're actually kind of increasing the amount of noise, as well as the fact that the geochemistry of flint is very pure over and very similar across large distances, so it becomes more and more similar, basically. What we also wanted to know was, can we boost the performance of individual sample sites, and whether adding more samples from those sites would help their performance. So for each of the different techniques, you can see here, we plotted the number of observations, so the number of samples against their score. basically what you can see is broadly a positive correlation showing that yes, like more samples equals better performance. So that's kind of quite important. So once we'd done those kind of smaller analyses, it was then time to evaluate the final models. So your random forest, k-nearest neighbor, and support vector machines. And to do that, we did a 10-fold stratified cross-validation. So i.e. we took 10% of the geological data, and that was stratified, i.e. we took an equal amount from each of the sample sites so as not to bias to sample sites with more samples. And then we tested the machine learning models 10 times using 10% each time. That way you've tested 100% of the geological data. What we found after doing that is that random forest was performing the best with an accuracy of 85%, followed closely by support vector machines and k-nearest neighbor. And these are all good, or very good results, but random forest is statistically significantly different from ANOVA when we looked at from k-nearest neighbor, sorry, from doing a classic ANOVA. So we have kind of more of a breakdown of the results. So along the top, we've got the kind of overall performance of those 10 models for each technique. And then along the bottom, we've got the individual performance of each geological site in terms of when you've taken that test data from it and then trying to put it back in that class or that geological site. So yeah, it's basically showing that some sites are performing really well, so like Flamborough Head, but others, there's a bit of a mixed bag between those different models, suggesting that they're really struggling. And again, we can look back then at the amount of samples, and then even within that, I'd collected from different flint bands. So it might be a case that actually separating them out further and collecting more samples for them will increase performance overall. Okay, so in terms of the conclusions for the paper, we found that we're onto the right track with using random forest, and that generally more geological sampling will help us boost the performance of these models, but there'll be diminishing returns. But where it will help is in helping those individual geological sample sites perform better, and that will help raise the average score of the machine learning models. At a kind of broader level, basically what it's showing is flint in Britain can be sourced. There's a bit of a myth that's kind of going around in British archaeology that you can't source flint. We've shown again, yes, you can. And in our case, we've shown with machine learning, you can get down to a much greater spatial resolution than has previously been possible. For the superficial deposit sites, actually what our kind of analyses have shown is that if we go back and collect more samples and then separate them out again, actually we should be able to include them in our kind of evaluations in future and provide more accurate results for your artifacts. As always, however, caution is still needed towards any data and analysis, and we've been talking about this today. So I need to look at issues of patination and taphonomic effects, so burning of flint, and whether that has a difference on the chemistry of the flint before I even get to it, analysing it with laser ablation. And I also need to go back and fine-tune the laser ablation methodology. Looking to the future, however, what we're also looking to do is maybe develop a website where you could visualize our geological data and maybe upload your own if you're a third-party user, and maybe provide classification results of your own in much the way that you would compare radiocarbon dates to your kind of existing archives. Okay, so briefly touching on the work I'm actually doing at the moment, I'm working with Matthew to kind of evaluate the previous approaches that have been done using laser ablation on Roman coins, and compare this importantly to how you're using it in comparison to other approaches and techniques. To that end, I'm particularly interested in two things specifically, which are depth profiling, so looking at changes in the chemistry of the coins from the surface into the heart of the coins themselves, as well as elemental mapping, which is basically looking at changes in different concentrations of elements across the surface of the coins. If I've got time, I think the plan is to go back and look at some of Matthew's legacy data sets in a bit more detail with machine learning to see if we can basically get the most out of them. However, I've been a little bit delayed starting in October, so we had problems with the instrument over the winter. But while this was happening, I'm kind of conducting my literature review. So I'm now focused on what we call fluence tuning, where you're basically working out what's the best energy for the laser to ablate the material you're looking at, and in particular for the elements that you're interested in. So at the moment, I'm also kind of just generally checking that the instrument's up and running and stable and happy. So I'm looking at the material standards, which is what you see in the SEM image above. Yeah, I guess the next steps are to actually analyze some coins. And yeah, you can follow us on Twitter. Thank you.
It's really exciting to see the possibilities of these techniques for sort of provenance materials which we didn't think were possible. And it's nice to have materials which, from a geological perspective, have where provenance is still something which we can aim towards as a sort of question which is really critical to the things we're asking. So kind of questions you're asking. So, any quick questions that please?
Really interesting new approaches, and nice to see those developing in other areas. A couple of quick queries. Is there any evidence that if you'd got like a bulk sample and used ICP-MS, you would have got a different result from the smaller volume that you get from laser ablation?
Yes.
And the second thing was, are you using semi-quantitative for the elements, or are you calibrating all 53 elements?
Yeah, so on that first issue, this is something that me and Matthew are kind of really looking into. Yeah, I mean, with ICP-MS, you are getting a bulk figure because you're taking more material. The nature of laser means that you are picking up on those kind of micro scale variations. The question then is interpreting the results. Is it actually that you've got actual variation going on and that's what you're seeing? Or is it the fact that you've got issues with delays in material coming through the pipe to the mass spectrometer, giving you different values through time? So yes, there's still issues around this, and that's what I'm really trying to understand with Matthew when we're looking at the coins. And yeah, what was
the semi-quantitative for the 53 elements?
Yeah, so I'd have to, yeah, so it was quantitative for all of them, I think. So we're calibrating to NIST 610 in the PhD. Yeah.
Further questions? Bruce.
This is wonderful to hear about this. I mean, I think it's highly desirable if there was to be further equipment of this type in this institution. But from the lithics part of your paper, the question I'm prompted to ask is, what's the take-up of using this, as it were, with colleagues in earth sciences? But in a sense, if there were more reference collections of data, that would be helpful archaeologically.
Well, so I guess as far as I'm aware, the BGS does have samples of flint, and actually Simon Chenery at the BGS worked with Paul Pettit on their laser ablation, looking at the upper Paleolithic material. But I guess this is the whole point. We need to generate some data sets from which we can then compare artifacts. And so this is what we've been looking at with the website, is that, you know, we've made this data set. You want other people to be able to use it. So I guess that's the kind of take-home message going forward, is that, you know, we've got the data, please use it.
Thank you. Last question.
So just one quick one. So what's going on the flint? The material that's moving furthest, what format does it take? So the assumption has always been that those pieces that are moving the greatest distance are curated pieces, I suppose, in terms of assemblages and things like that. Is that what you find in terms of the Mesolithic?
I mean, I guess that's the idea, but how you provide any certainty on that, I don't know. I think, as we've touched on earlier, there's a tendency to feel like the science is giving you a kind of definitive answer, but I think what it's actually highlighting is that we perhaps need to be a little bit more careful about how we're interpreting the data itself to begin with. So I'm just trying to think of an example. So yes, in my PhD, I really looked into the problems to do with Binford's idea of embedded procurement, and especially this kind of dichotomy between mobility, i.e. people moving the materials around, and exchange. And I think in sort of Paleolithic and Mesolithic archaeology, there's still this tendency to think of it as mobility, as that's the safe option to interpret. And exchange is, we'll need more evidence to support the idea of exchange. And I think where I'm broadly at the moment is actually it's both. I mean, where you've got humans, you've got movement, and you've probably got exchange going on. So I don't think it's one or the other. I think it's both. And then I think it's probably on aggregate. You know, once you start to see lots of sourcing study results, maybe then we can then come back to, is it one or the other?
Fantastic. Well, Tom, thanks very much indeed. Right, well, it's me next, so I'll introduce myself very briefly. It's me, and I'm going to have to go relatively quickly. So I've set myself a bit of a challenge now, because we've promised to be out in good time. So you're going to have a compressed version, so compressed leather, and I'll hope that it will be quick enough to at least to convey some of the things that we've been doing over the last couple of years, looking at leather in Scythian period societies, I should say. So I'm just going, for some reason that's gone. Interesting. No, it's not that. Oh, I know, it's because it's set up. There we go. That'll do. Right, so this talk is a talk which is built on work which is funded by the Society of Antiquaries of London, and it was a project which was relatively small, which kicked off with me and my colleague in St. Petersburg and Moscow, who is now working at the Institute of History and Material Culture in the Russian Academy of Sciences, Barbara Busova, and some colleagues, ultimately colleagues in the Max Planck Institute as well, who've enabled us to expand this project into something a little bit more sort of a little bit larger, really. And it's built on the idea that we were really interested in the way that people were using costume. And costume, of course, is one of the most critical things that we have available to us as markers of who we are and what we want other people to think about. It conveys ideas about the way I'm going to take this off. It conveys ideas about the way in which we see the world and we see ourselves in it. And we want to present that face to others. I mean, there's a very different sort of perspective. We see people like this chap in a white suit on a bench, and he says something very specific about himself. I won't say what it is, but it's something very specific. Similarly, the presentation that you have when you have presidents presenting themselves as being a particular type of individual, says something about what they want to convey. And that's true in the past as well. And we see that costume is something which is depicted very often in the material culture available to us in the ancient world. So here, Persepolis from the eastern doorway, where you have numerous different ethnic communities being represented by their costume effectively. There's lots of different characteristics, and the ones in green here are shown who are associated with more or less specifically with the world of the Eurasian steppe. In the Greek world, we see again peoples who are characterized as being depicted in very standardized ways. Whether or not these are actually Scythians is a bit of a sort of debatable point, but certainly they're showing up this importance of costume, and quite elaborate costume, as a feature of particular communities. Let's just emphasize the same point. Within these societies themselves, though material probably made for rather than by them in this case, this is a Kulabar, the cup from the golden cup from the Kulabar burial mound in southern Ukraine. You're seeing again the same kinds of costume, but depicted in perhaps a more authentic way in terms of the way in which they're put together, as we'll see a little bit later on. And this gives us an insight into the kind of things which might be important. We see this from texts, of course, as well. We've got lots of things which describe the kind of things we might be looking for. And this leather features very strong. This is from the Shiji Chinese text, which describes from the king downwards, they all ate the flesh of domestic animals and covered themselves with skins all over. Other sources giving us ideas about what kinds of skins we might have. And of course, Herodotus giving us a somewhat more grisly tale of human hands being used as quiver covers and scalps for their coats. That's a little bit unrealistic, but we were open to the possibility that might be an accurate depiction of the of Scythian leather use in the past, and so it was something which we thought might be worth at least having a look at. Maybe not that open to that idea, to be honest, but so we started looking at this question in an area which has been extensively studied in Russian archaeology for many decades, indeed for centuries. The area which encompasses the Altai Mountains and the Middle Yenisei Basin, which is highlighted there for you in the circle. A large area, of course. And this is the first time we've really begun to kind of look at this. And my colleague, Barbara, has been working on this for some time, has been looking at microscopic techniques for identification. We began to sort of look at other ways we might deal with more challenging material within that set, as well as refining the work that she's been doing on that subject. As I say, this has been a subject of study for a long time as archaeological material, but these kind of organic materials tend to get much less interest than the extraordinary metalwork and the sites from which they come. It's an area which is full of gigantic mounds, some of which are hundreds of meters across, and which stand, as you see from my colleagues Jade and Yuri there, underneath one of the corner slabs from the Bolshoi Salvitsky Kurgan, which shows up the scale at which we're talking. This is a model of the kurgan itself. You're seeing just one of those corner slabs there. It's an area which is famous for its gold. It's famous for very shiny, very exciting types of burial. Here, the Arjan and Arjan II kurgans in the Tuva Republic, showing off one of which buried with 20 kilograms or something of gold in its mix. This is an important finds from a point of view of making archaeology exciting. And it's very rare now. I think it's mandatory that any talk on Eurasia includes Arjan II as one part of its discussion. Otherwise, I assume that would be illegal. So here we have two of the individuals reconstructed with exciting costumes made of various textiles, including golden embroidered trousers. This is big stuff. But actually, there's much more going on here, which we thought we could investigate. Not just these big shiny graves, but lots of other smaller scale burials, lots of other sort of what my colleagues call middle class burials. They like retaining a certain sense of irony in the term, but looking at societies of normal people and what they were doing in their lives, the kind of normal people who were really being described both from the king downwards by the Shuji and probably by Herodotus as being rather sort of clad in leather and so forth. And this does seem to be brought out in terms of the leather bit, at least broadly. We find all kinds of materials being represented and produced by them. and used in all kinds of different ways. We find complexes of leather preserved primarily, in most of these contexts, preserved in association with metal. So where the metal is preserving it, it's providing a biocidal environment which allows it to survive. In other cases, it's particular specific contexts where we get amazing preservation thanks to chance sort of occurrences where well-sealed coffin burials are preserved in a dryish environment and have been protected to some degree from the sort of normal taphonomic processes. We see really very striking preservation of particular assemblages. And here you see a young girl preserved with, and you can see not only the skin of sort of much of the skin of the body preserved, but actually also the skin of the leather clothing in which she was dressed. More famously, perhaps, you have preservation in ice, of course, very excitingly, and the famous tombs at Pazyryk in the Altai Mountains, where you're seeing these chance freezing events which led to the formation of permafrost within the tombs themselves and its preservation over long periods of time. And you see here all of the organic material preserved in those burials being carefully excavated here just after their discovery. What does this material look like then? Well, I won't go through too many examples, but you're seeing the kind of thing we're finding are wide variety of material, everything from sheaths to small pouches and bags and clothing, quivers of various kinds, accoutrements, all mixed together I seem to have left all my slides in here. I thought I'd cut these out. So lots of things like belts and up to clothes and other forms of covering, not only for humans, but also for animals as well. Very exciting. You hear that's the reconstruction of one of the horses from Bray in eastern Kazakhstan. And what was interesting about these, apart from they're obviously rather cool, is that they seem to be combining materials in lots of interesting ways. You're seeing not only leather, but like wool, relatively sort of a relatively new material in the sense of textiles, actually being combined in lots of ways with these leathers. Leathers which appear to be perhaps showing something about the way in which people were using them, thinking about the way in which people were using natural and domesticated resources. We felt there were lots of questions there to be asked. And not just combinations with organic materials, thinking about people bringing together different types of materials together from inorganic and organic materials. Here, two examples, leather objects painted with hematite and cinnabar, found in different contexts, and thinking about the ways which you might begin to sort of study. That wasn't a major focus of the project, but it was one which we were able to kind of develop a little bit by some sort of targeted analyses there. As I said, my colleague's been working for a while on this, thinking about the microscopic identification, and it's a subject which has been studied for many years, really, in places like the Leather Conservation Centre in Northampton, where you have thousands of comparative samples to work with. But the problem which we were encountering was actually the preservation of this, although it appears very good, is often quite superficial. It looks good, but underneath that sort of goodness is a degradation which actually prevents clear identification. And so we decided that we were going to try to sort of a different approach, looking at peptide mass fingerprinting, zooms, and applying it to these leather items to see if we could really get a sense of the range of animals being used from not only from the best preserved objects, but from sort of the less well preserved items. So here's my colleague Barbara and Samantha working to place our process samples onto the plates ready for analysis. And for those who don't know, a very quick view, zooms is a technique which breaks down which extracts collagen, breaks it down into predictable peptide fragments, and based on studies allows us to form libraries with which we can compare unknown samples. That's the horribly brief version of that, but it's all we're going to get for the moment. Basically, it allows you to identify species or groups of species are based on the composition of their collagen, or the way their collagen breaks down. There we go, that one's a cow. So we took about 104 different objects, about 140 samples. The results, very briefly, predominantly domestic, unsurprisingly, but with some wild species represented in well, particularly with an interesting kind of addition of various fur-bearing species as we would expect. But what we were interested to look at was some interesting kind of features of these, and we found that there were quite a lot which weren't matching anything in this relatively well-established library, including particularly rather large numbers of thread, which is an question which I'm not going to answer today, but it is an interesting problem that thread or sinew doesn't seem to match any of the obvious candidates for its production at the moment. So we're trying to work out why that is, and that will be a future sort of study. But what we were seeing is interesting combinations which make lots of sense in terms of the way in which they're using these leathers, demonstrating these sort of skill sets of working. You're seeing here a bag from Potlatch, where you're seeing the use of horse as the main substrate for the bag itself, ornamented with goat leather and with an unknown or animal source thread tying it all together, actually containing within it as well a big sort of mass of sinew, which was sort of there for future use. You see lots of practical choices, the things we'd expect to find, leathers sort of routine, a relatively wide range of leathers being used for routine tasks for sort of normal objects. Thick leathers where you'd expect to see thick leathers, thin leathers where you'd expect to see thinner ones as appliques and so forth. But we're seeing them being combined in interesting ways, not just due to a sort of single animal for an individual object, but using like thick parts of plough leather for the bases of quivers very consistently, and then various different animals for the panels of the sides, combining them with wood as well and pigments at the same time. We're seeing complex processes not only in the selection of materials, but in their deployment in objects to enable them to kind of not only give different patterns, but also maybe to give different properties to the leggings themselves. This is a pair of trousers, or one leg of a pair of trousers from Tuitka, and you're seeing this multi-part pieces of sort of little squares of material being sewn together in really interesting ways, combined with very, very finely worked appliques all the way across. And all of these materials are being made from different types of animals. We're seeing everything from sort of foal leather to the front of the thing, this black strip with hair on fur, intact leather, and we're seeing these sort of smaller appliques on the sides. Not dissimilar, I would point out, from this, the Coulabas sort of cut that we saw before, where the stitching on the individual patterns of the trousers are actually shown quite clearly, and is something which I think is a good question, probably providing some stretch. The tight-fitting Scythian leggings that you're seeing there, made up from stretchy sinew stitched together with multiple parts, something which is maybe worth trying, although I'm not volunteering to put on a pair of Scythian leggings. I don't think they'd suit me. Sort of thinking the most sort of highlight examples, of course, come from those fancy tombs. But they're not necessarily, to me, the most exciting results of thinking more about those broader characteristics of animal use, which show up are the kind of patterns that we're seeing from ethnographic sources, where we see specific animal types being used for specific things at specific times of year. For example, bowstrings from Tuva in the 18th century was recorded the use of different animals to create bowstring tendons at different times of different seasons, looking into those properties of leather and real kind of subtle understandings of the way they behave. Less subtle, but rather exciting, of course, is the use of kind of multiple animals in these extreme examples here from Pazarika bag, intended for cheese, where you have a goat leather base being applied onto it, this indigo and indigo dyed deer leather, a further sort of hair on sheepskin, and oops, there he goes. I'll put him back there. Oh, he doesn't want to stay. He's a fleeting snow leopard. You have to trust me. So there's these patches here of snow leopard and fur as well on the sides. This is a fancy bags. Equally exciting, I think probably more interesting for me though, are things like these kind of the sort of hints that we get there's something interesting going on with these unknown samples. Because a previous study which we were comparing with and hoping to find confirmation for in this cell analysis had shown that one of these coats, these fur coats of this young girl, was actually made from the skins of jerboa, a rather small animal to be making skins from perhaps, but one which is at least very readily available in the environment. And it struck me as being a particularly exciting sort of window into these societies, that they're not covering themselves in the hands of their enemies, but these sort of Hell's Angels of the steppe in the Iron Age are actually dressed up with mice. And for that, that'll end the conference, I think, for today. I would love to take questions, but I have promised to be out of here in good time. So can I ask that we ask them in the open air? Thank you. And can I also thank all of our speakers today? You've been fantastic, and thanks to our audience for coming today. It's been great to have you all here in person. And everyone who came online and stuck with us as well. We've had a pretty stable group all day, so thanks to everyone.